and TopCon, Dr. Ted Lang from Byers Eye Institute at Stanford University in Palo Alto, California, Dr. Jennifer Lim from Illinois Eye and Ear Infirmary in Chicago, and I am Dr. Rishi Singh from Mass Eye and Ear in Boston. And we have a ton of speakers joining us today, and I'm going to show you their picture in just a second. Here they all are. These beautiful faces and names today are going to really educate us on the beginnings and ends of AI. And you can see that they're a conglomeration of both academic institutions and also some of our premier pharmaceutical companies, as well as imaging companies that are going to be presenting here today. Because AI is cross-cutting in many ways and really working on many different fronts, we thought that would be the best way of bringing this to you is really to show you the depth and breadth of where this is happening in our ecosystem. Thank you to our sponsors, Apellis and Genentech, for their sponsorship for this meeting. We will be doing Q&A during this meeting, so feel free to ask questions. Just like in Zoom, you go in the bottom here, there's a chat box, and you can enter right in there a question. We have a panel discussion coming up, and we'd love to take your questions as part of it. So let's get started with our first talk. This is going to be the session one, Technological Advances in AI from Data to Solutions. And we're going to start our first talk with Dan Ting. Dan is coming to us from Singapore. And Dan, thank you for joining us from remote your location. He's going to talk about generative AI in ophthalmology, latest trends in 2026.
Thanks, Rishi, for the kind invite to share. Hi, everyone. I'm gonna spend the next 8 minutes to talk uh, to you guys about all the different latest trend in Gen AI ophthalmology. This is some of my financial disclosure. I'm just trying to advance my slides from my side. Not sure whether you guys can hear me.
We
All
can
right,
hear you.
so this is chat. Currently, we are in the chat 5.5, and it started in 3.5 just 3 years ago. And right now, for Meta, we are currently in the Llama 4.0, and for Gemini, we are currently in the 3.1, the version 5, the era right now as we speak. So as you can tell, many things has happened for the last 3 years, and this trend will continue to evolve in the highly rapid manner for the next many months or many years to come. And I'm sure a lot of the people in the audience would have had patients coming to you with many different Gen AI engines responses, telling you what to do, and some of them would even would insist on what you actually provide them. So this is the current era that we are talking about the patient's care in the routine eye clinic. The next question is about the use of agentic AI. The reason why I use the word agentic is because right now the AI has the capabilities to think and even prescribe actions themselves. In the past, when we started doing AI, it's just a bunch of the imaging with the label ground truth to use them as a training data sets and the AI algorithm, looking at the similar examples. Now, if you look at the use of agentic AI and incorporate them into your EHR, to your imaging in your surgical devices, they could potentially be very powerful. This then lead us to the questions. Is that gonna make us supernumerary? Is AI going to replace us? I think this is an existential questions that many people would be asking us, and or if whether or not AI would make us more efficient, right? We see 100 patients a clinic now with AI, or if whether or not AI can make us smarter clinicians to diagnose the things that we are not being trained for. So I think this is some of the recurring questions that we always have with the current agentic AI solutions. We are talking about the next phase of the use in AI. That would be, how are we going to train our current fellows or residents? So in I, we always train our current fellows with the different subspecialty, cataract, complex cataract surgeries, glaucoma, tube implants, and stuff like that. How are we going to teach AI to the retina fellows and residents right now? Are we going to teach them as per how we are teaching them in terms of analyzing the OCT, which is a very basic skill set that all the general ophthalmologists should have? For AI, can we actually then use AI to accelerate some of the medical product lives, right patients for the right treatments, for the right trials? The second question is, can we actually use AI to decentralize some of the clinical trials? So instead of recruiting them in the routine eye clinics, can we actually recruit them from the community? And if we go one more steps upstream, can we even use AI to identify potential molecules for drug discovery? This is a very common questions that many startups or biotech pharmaceutical advisory boards that I sit in that often get asked. Is it cheaper to build or is it cheaper to buy? If I'm the Genentech CEO or if I'm a Roche CEO, how do I recruit the next generations or the current generation of my staff? Do they all need to have AI or digital literacy? Because hiring one staff, is it much more, one staff with AI capability, is it more worthwhile or more worth it to actually as compared to hiring 10 different staff with no AI skill sets? I think this is some of the ROI questions that we are actually often getting now from the industries. And last but not least, are we currently in Industrial Revolutions 5.0? I don't think many people have talked about Industry Revolution 5.0. We are all stopped at 4.0, but I do think that we are currently in 5.0. If you look at the Nobel Prize winners in 2024, 3 of them belong to the AI computer science, the space. And right now, globally, I think we are experiencing a very intense AI race. The AI race happens not just within the technology companies, it's also happening between the countries. And we know recently President Trump has also led a group of the technology CEOs to China to visit President Xi. And if you look at the different large language model engines in 2026, we can actually broadly divide them into the closed source and open source in the tiny, small, intermediate, and large models. So depending on the research questions or business unmet needs, we have to choose the right models for the right use. And that also highly related to the AI and also the data sovereignty. This is some of the past papers that we have published in the Nature Medicine and Ophthalmology Science, both in the general medical domains and the ophthalmology domains. So large language model is pretty good in now summarizing and organizing the contents, generating the draft, the contents, and we have not quite seen the first FDA approved the clinical decision support tool using Gen AI as a backbone. But I think in the next 3 years' time, we will potentially can see some of that being approved. Agentic AI is simply means that the AI can now automatically think and achieve goals based on their own assessment without the constant human side, as opposed to the traditional AI model, how we train it. Medical superintelligence is a term coined by Microsoft just short of 12 months ago. And it means that using agentic AI, they can potentially solve complex medical diagnoses. And this is one of the examples they use to show that the AI has 4 times higher the accuracy rate as compared to the physicians in solving complex medical diagnoses in the NEJM CPC cases. This is the second paper that shows that the physician who use AI will perform those who do not use AI. So then the questions now remains, in the future, the physician who do not use AI, would they be deemed unethical because of the safety issues? We talked about safe and responsible AI. This is one of the paper that we published last year in October in Nature Medicine. We proposed a framework called the SAFER framework. So SAFER basically means safety, accuracy, fairness, and ethics, ease of use, and return on investment. In addition to that, the AI regulations, whether it's going to be considered as a SAMD or non-SAMD, software as a medical device, the AI explainability, the AI governance issues to consider when we talk about safe and responsible use for AI in healthcare and ophthalmology. The last slide is that eye superintelligence. Can we see that coming in 10 years' time? So today, if I inject the AI with the patient medical history, the risk profiles, with the patient's imaging such as fundus photos, OCTs, Optos white fields, genetics profiles, and microbiomes, not only using the patient cross-section data, but also the past data, can we actually predict the future, and can AI actually diagnose the conditions correctly and also the actions correctly? This is something is super exciting to know and find out. So with this, I would like to thank the organizer for the kind.
Thank you. Thanks, Dan. Appreciate it. So we're going to go on to the next talk, and we'll have a chance to really talk about this presentation you gave. It's very aspirational in nature. I love the way you phrased it. Let's turn it over to Dr. Tobias Els. He's at Mass Eye and Ear Infirmary. He's talking to discuss building the future for ophthalmic AI, our institutional data and imaging repository.
Yep, thank you very much. Let me see if I can proceed the slides. I need permission for, oh yeah, it works. Okay. It's just slow. Okay, sorry. Yeah, so I'd like to talk about the future of ophthalmic AI. And what do I mean by that future? This is actually the future about data for ophthalmic AI, because at our hospital systems, we are actually sitting on a treasure. And that treasure is not crude oil like here. It's actually the enormous amount of existing patient data. And like the crude oil, it's sitting in the ground, or maybe not in the ground, but on like opaque imaging systems or difficult ophthalmic machines, etc. But unfortunately, we don't have drilling equipment available. So each institution needs to develop their own sophisticated engineering skills to to use their own data. This is the present. That's how it is right now. So there's, oh yeah, and we at Mass Eye and Ear, for this purpose, we teamed up for this purpose exactly. That means John Miller as Director of Retinal Imaging, Nasli Zebadas, Director of Glaucoma Imaging, and myself for the implementation. And we set up the Mass Eye and Ear data repository with a goal to make every single measurement which has ever been done at Mass Eye and Ear available for research purposes. That includes demographics, diagnoses, procedures, measurements of visual functions, and of course, retinal imaging. And here we can see the four major sources of our repository where we get the data from. This includes EPIC for medical records and 3 different centralized imaging systems. Let's start with EPIC, which we access through a database backend, a Snowflake database backend, which allows us to mine not only our own over 2 million mass ear patients, but even the nearly 11 million patients of our large hospital consortium, Mass General Brigham. So that means we can trace each of our mass ear patients throughout all the different hospitals of that hospital consortium where they are treated, which gives us a great opportunity for cross-disease research, oculomics, etc. Yeah, that was about electronic health records. What about imaging? For imaging, we access 3 different picture archiving and communication systems, so-called PACS systems. And if you hear their names like Zeiss Forum, Topcon Harmony, Heidelberg HiX2, you're probably associating their fancy front ends with these systems, which you can easily access from your PC, from your office, to look up your own patient data. For this purpose, they are great. They are not so great. Actually, they are nearly unusable for large-scale data export. So instead of accessing the front ends, what we are doing is we are accessing the file server backends of these systems in a fully automated way without the need of human interaction. That sounds great, but it comes with a big challenge. It's actually not forbidden by the manufacturers to use the file server backends, but there's no documentation at all. So we had to develop our own custom software in-house for this purpose. And this custom software helped us so far to export over 500,000 Humphrey visual fields, over 4 million fundus images, over 1.3 million Cirrus and 2.2 million Spectralis OCT scans, and all of that in a fully automated manner with automated weekly updates in place. So how it works, usually it's every Friday after office hours, the software identifies all the new scans, visual fields, fundus images, etc., which have been obtained over the week, grabs them and automatically integrates them into the repository. So now you might wonder, okay, that's great that these guys have that at Mass Ear. I'm not at Mass Ear. How can I benefit from that? And then here it gets interesting for you, because you might have heard about the SOURCE Consortium, which is a large consortium of academic ophthalmology departments for sharing EHR data, which is centrally managed at the University of Michigan by Josh Stein. And as I just mentioned, the source is right now focused on EHR data. And Josh and I, we are in the process actually of including imaging data into the source. For this purpose, we are in contact with about 20 different source sites. And here's the setup. We would like to implement. This is all in process. So each site would actually implement exactly the same data and imaging infrastructure as we have it at Mass Ear. And for this purpose, we strictly separate the metadata from the actual imaging data. So metadata, that means not only the medical record numbers or the date of the measurements or the machine, it can also mean derived measurements such as, for instance, retinal nerve fiber layer thickness sectors or ETDRS grid thicknesses, etc. Whatever is simple non-imaging data easily available. And all these metadata get actually transferred automatically to the source, whereas the images themselves remain local at each institution. Now you might wonder, okay, if the images remain local and are not centralized, what's actually the purpose of that? There's still a large potential usage for that, because one thing you know for sure is you have exactly the same data structures at each of those institutions. And yeah, so the metadata can be queried in a centralized way. So for instance, if you have an AMD project, just imagine, yeah, so, and you would like to know which institution has which kind of OCT data from which machine, which protocols, how many A scans, B scans, etc., you can query that centrally through the source. Then you know exactly which institution has what. And then instead of making a data usage agreement with this institution, you could develop your own local data analysis software, send it over to that institution, and they run it for you and give you back the results. And this is only possible because you know exactly how the data structures look like at each institution. This is also a like condition, necessary condition for all kinds of federated learning. And if you guys at your institution are interested in setting up something similar, feel free to get in touch with me. We are very happy to talk about that. Thank you very much for your attention.
Thank you, Tobias. Well, that's really an eye-opening conversation to kind of all of the data that's out there and what we might be able to do with it. So we're gonna have people comment during the Q&A and love to have you stay on for that. And it's coming up. And again, for those watching, you can put the question box in the Q&A and we'd love to take your questions toward the end. And now we're going to go on to the next talk by Minaj Alam. Dr. Alam is going to speak on federated learning for ophthalmic diagnostics.
Hello, everyone. Good morning. Really excited to be here and thank you for the invitation. I think after the last talk, this is kind of a very nice transition into talking about federated learning. Um, so, in today's talk, I'm going to talk mostly about two fundamental challenges in federated learning, mostly on the algorithmic side, which can be really, really useful when we apply that for ophthalmic diagnostics. My name is Minhaj. I'm an assistant professor at UNC Charlotte. Let's see. Next slide, please. Okay, got it. Um, So I think most of the audience is quite familiar with federated learning. It's a machine learning technique where you have multiple decentralized nodes. So in here we can talk about clinics who collaboratively train a model, and the data stays local. So it's like very interesting concept where we solve a lot of privacy and compliance issue. On the other hand, the model gets access to a huge variety of data sets, or at least trained on those weights based on this data set. So the model generalizability also improves quite a bit. So there's basically a really, really big clinical need for a robust AI model training framework that can leverage multi-institutional data without compromising data sharing concerns. So essentially, federated learning also provides, on top of data privacy and security, a capability of multitask learning, which is what real life clinic actually does, right? A patient comes in, we just don't say binary classification like disease versus non-disease. We have to go through differential diagnosis, and federated learning really helps individual local institutions kind of focus on what they care about more in that aspect, in the diagnostic part. So our lab has already extensively demonstrated the efficacy of federated learning in ophthalmic AI, and also the community has done quite a bit of work on that. So thanks to a lot of collaboration and like a multi-site studies. So we have demonstrated federated learning can improve model diagnostic accuracy, and also the model transferability or generalizability across sites. We have compared them to performances of like local models versus centralized models. We also demonstrated that because there's a lot of data coming from different device, demographic population, so domain adaptive federated learning with some sort of pre-training mechanism can actually really improve the model performance, even similar to a centralized model where model has access to all data. So the summary of findings so far is Federated learning outperforms any local model for uh, validation across sites. Um, Domain adaptive federated learning delivers a performance boost, really great generalization. Some sort of pre-training like self-supervision can actually help federated learning to kind of help with the data heterogeneity, improved privacy, and performance. So so two fundamental challenges we have observed through our recent work. One is the difficulty of model aggregation. So retinal image distribution can differ based on different device, demographic population. So there is a problem of data heterogeneity, domain shift, and personalization. If the domain alignment is too much, the model loses some information, so local models get hurt. The second challenge is label scarcity and sometimes noisy labels, which is a major challenge. So labeling and noisy labeling is also very problematic. So if I talk about the challenge one, which is the global versus local performance, so this is a study that we recently did where we know we said that we kind of identified that because of the difference in vendor protocol, demographic population, that different generic averaging of federated learning weights does not yield the best result. And oftentimes, because we're trying to maximize or optimize the external performance, let's say we're trying to make the model very generalized, the local model or the local institution might kind of suffer from that. Let's say if an institution has a large number of data sets and really good distribution, because the federated learning framework optimizes on generalizing. So let's say if you really are caring about a certain disease or generalize a certain classification or diagnosis in your local institution, so that might hurt. So there's like a trade-off between how much global your model should perform, how much local you should perform. So we kind of came up with a tricky data aware aggregation that also preserve local performance compared to a widespread global performance on different AI tasks like diabetic retinopathy staging, progression prediction, etc. So call this FedSim. We call this eigenfeature aggregation. Essentially, we extract the eigenfeatures of the model and use that to kind of build up this data aware aggregation strategy that is shared across sites. The idea was basically we want to make sure that the model but is model eigenweights are normalized so that when the model is optimizing very much on the global side, the local features also are preserved for any client specific tasks. And we demonstrated that compared to Fed average and Fed prox and some other baseline federated aggregation methods, we perform well across like global tasks and local tasks. The challenge two is noise and incorrect labels in federated learning. So this is just an example where you can see like a horse is labeled as a dog, horse is labeled as a frog, the car is labeled as a truck. So this is an example of noisy labels. And this can be very similar in like, let's say OCT imaging where because of ICD-10, the label can be wrong, or it could be a mistake or some other reasons. So because of these noisy labels, model performance really gets affected. So we saw that the noisy labels generally leaves a fingerprint. So what this means is that for each class, basically we form a feature matrix from all class samples, and then we extract this feature direction. So in clean clients, different classes occupy distinct directions. So off-diagonal entries are kind of low, but if it's there's a lot of noisy labels, the off-diagonal similarities arise. So we use this kind of hypothesis and identify this kind of basically there's three stages where we identify class subspace similarity, we fit on spectral statistics, and we use this spectral geometry to actually correct labels. So basically almost think of it like a mapping. If one client has very nice clean labels, it creates a map of those labels. Let's say diabetic retinopathy, NPDR or mild NPDR. And then other client has noisy labels. So the noisy labels are aligned with the clean label spectrum. So basically by this, we not only identify clients with noisy labels, but also correct noisy labels based on their spectral geometry. And we kind of played around with how much Noisian label can be. We simulated that using this alpha parameter. So alpha 0.1 is lower noise. We kind of kept increasing, and we saw that all the way up to like 0. Like 50% of the data is noisy, and our aggregation method was providing very nice accuracy. So the take-home message is essentially distributed approaches like federated learning are really beneficial for training large-scale, multitask foundational AI models. And it's crucial to identify and address the scientific and fundamental limitations, which we are trying to do. And again, model validation and pilot clinical deployment are still really necessary for real-world feedback. So with that, thank you so much. Happy to talk during the session.
Thank
Thank you.
you. Great talk. Thank you very much. And love to get to the Q&A. And there's some questions coming in already, so it's great to see that. And we'll definitely be able to chat with you in short order. We're going to go to a recorded presentation by Dr. Keene. Dr. Keene couldn't be here with us today, but he's going to talk about foundational models from artificial gene and general intelligence to artificial medical intelligence.
Hello, everyone. My name is Pierce Keene, and today I'm going to be talking about foundation models and how they may play a key role in going from artificial general intelligence to artificial medical intelligence. So my background is that I'm a consultant ophthalmologist and retinal specialist at Moorfields Eye Hospital in London. I'm also a professor of artificial medical intelligence at University College London Institute of Ophthalmology. And so I use the term artificial medical intelligence because I'm very interested in the advances in AI outside healthcare and efforts to try to achieve what is called artificial general intelligence, or AGI. And this is essentially a state where we have AI models that are as proficient and as versatile as humans in most cognitive tasks. And so I'm very interested in what that means when AGI comes to healthcare, which I call artificial medical intelligence. Now, I'm fortunate to be funded by UK Research and Innovation, and these are my financial disclosures. So foundation models is one of the key areas that's been at the center of recent advances in AI. It's a term that I first came across when I read The Economist in July 2022, and was originally coined in 2021 in a preprint from a group of researchers led from Stanford. And The Economist talked about how huge foundation models are turbocharging AI progress. And essentially, these are models that are trained on huge amounts of data, and then one model can act as a foundation for multiple other models, which can be fine-tuned for different downstream tasks. Now, the key aspect about these models is that they typically use a new type of neural network architecture, which is called the transformer architecture. And this was first described in a paper from Google in 2017, one of the, I guess, most widely cited papers in this field. The other aspect is that they use a different approach to learning. And so they typically use something called self-supervised learning, which is a kind of unsupervised learning. So essentially, the big advantage of these models is that they can be pre-trained on huge amounts of unlabeled data, and then they can be fine-tuned with much smaller amounts of labeled data. And this opens up applications in a wide variety of hitherto unlooked at medical use cases. Now, we created something called RetFound for Retinal Foundation, which is the first foundation model in ophthalmology and one of the first across any medical specialty. We published this in September 2023 in Nature, and this is the work of Yukun Zhou, who's a postdoc working with me at UCL. And one of the things that we're most proud about in this work is that we made the model code and the model weights open source. And so we're seeing researchers around the world using the model and trying to improve on the model that we made available in 2023. Now, we're already starting to see some real-world research studies. We're working with a great guy called Steve Brahman, who is essentially seeing how he can do trials of this in a research setting in a rural Bangladeshi context. We're also trying to think about what the next steps are in terms of foundation models and how we can go global and create something that we call Global RetFound, which is our effort to try to build the world's first truly global foundation model. And working with Yicheng Tam and Carol Chung and great teams from Hong Kong and Singapore, our idea is, could we develop a foundation model on 100 million images from 100 different countries, and again, make this open source for non-commercial use at the end of it? Now, this is a pretty ambitious and one might even say grandiose plan, but the way that we intend to do it is to train the model using a combination of real and synthetic images. Now, the other thing that I'm quite interested in is looking at the foundation of foundation models. So what I mean by that is looking at the science behind these models. And in particular, we're working to look at pre-training data effects in these models. So for example, if someone approached you as an AI developer and said, we have 1 million retinal photographs from a certain context, and someone else approached you and said, we also have 1 million retinal photographs, how would you decide which would be the better data set to pre-train on? And so in this paper that we published in Nature Communications in February, we essentially trained two identical foundation models. So using the exact same sized retinal fundus photographic data sets, about 1 million images, and we using the same training and learning approaches, and we trained a foundation model in London, and we trained a foundation model in Shanghai, and we looked at the differences in the pre-training data. And actually, one of the key points about this was that age and the age associated with those images seemed to have the biggest effect, and much more so than other things that you might expect, like sex or ethnicity. The other thing that I'm quite interested in is how foundation models can be used for drug discovery. Daphne Kohler is the founder of a company called Incitro. She's a legend in the field of computer science. And so last year at Moorfields, we announced a collaboration between the Insight Health Data Research Hub at Moorfields and Daphne's company, Incitro. And the idea was that we would work together to develop a foundation model using data at Moorfields, and that would be then used for internal research and development efforts by Incitro. So we have actually created this model, and we call it I-Know V3. And the key thing about this model is it's based on the state-of-the-art in computer vision, which is the I-Know V3 model from Meta. We've trained it with more than 100 times more data than the original RetFound model, and we're also training it on full volume OCT data. Now, we haven't published the results on this yet, but we did present a poster of the work at ARVO just a few weeks ago. And so just highlighting the exciting thing about this is that it's been trained on about 140 million OCTB scans using this approach. Now, where are foundation models going next? Well, there's a lot of different areas, but I think one related area is how they can be paired with the context of something called agentic AI systems. Now, for anyone who hasn't heard much about this, I highly recommend this essay written in The Lancet in February 2025 that speculates about the future of agentic AI in medicine. Now, the key thing about agentic systems is that in non-agentic systems, you typically have a user that gives a specific command for a specific output, and then you combine the outputs to complete a task. In the context of an agentic system, the user, such as a doctor, simply gives a high-level goal, and then the AI creates a plan and executes multiple steps in autonomous fashion. Now, the analogy that I would use is the thermostat in your house. So in a narrow AI setting, you would essentially just say to it, try to get a temperature of 21 degrees, and then the system would raise or lower the heating to try and achieve this. With an agentic analog of this, you wouldn't say that. You might give a high-level goal, which is, make the temperature in the house comfortable in an energy-efficient way. And then a range of different narrow AI agents would look at things like weather forecast, energy prices, your schedule, the appliances that you have, and coordinate things autonomously to ensure that you're always in a kind of balmy environment, and of course, cost-efficient environment. Now, we're still in the early stages of seeing agentic systems in healthcare. We've created one of the first of these in the context of ophthalmology. We call it Off Agent. This is the brainchild of Li Zhu, who's a postdoc in our group in UCL and previously did his PhD in Monash University in Australia. And so we've got a paper under review which looks at this. There's also a preprint available that you can look at. And essentially this takes a range of different AI agents and coordinates them in an agentic system. One of the things we're excited about with this study is that we've done a multi-case, multi-reader study with over 300 physicians from 80 different centers. So as I say, hopefully that will be published soon. But in the meantime, please check out the preprint online. So what are the next steps in terms of foundation models and generally with AI? Well, I think one of the interesting things is what happens when we scale these up, particularly in terms of the size of the models, particularly in terms of the size of the data, and particularly when we incorporate synthetic data. I think there's a lot of unresolved scientific questions around the different pre-training methods and how you evaluate pre-training. I think we're also quite interested in how we can make more lightweight models that can be deployed on the edge. And then I think a big kind of existential question is, what is the role of generalist models, such as models like I-Know V3 created by the hyperscalers, the frontier labs, versus models that are more refined in the context of specialist data, such as ophthalmic imaging. And then the last thing that I'm kind of interested in is how can we start thinking about translating these in the future? What are the regulatory considerations, for example, if you're incorporating a foundation model into a future software as a medical device? So that was a short canter through this from me. If anyone would like to get in touch, that's my email address. Thank you very much.
Yeah, thank you. Thank you, Dr. Keene. Dr. Keene couldn't be with us today, but thank you for that wonderful presentation. We're going to go on and talk to Stephanie Campbell. Dr. Campbell works with Opco Health, and she's going to talk about patient-facing AI. When should we not use it?
Oh, thank you very much, Dr. Singh, for the invitation and for the opportunity to present some ideas. It's a real privilege to help kick off this summit in this first session and to provide some thinking around the contextual basis for the AI that we're all working so hard to develop. Because it's without doubt that the models and the technologies that are being developed and that we're discussing are really driving us toward optimized treatment planning. And we're rapidly moving from the standardization aspects of AI into the personalization aspects of AI. And without doubt, this is going to drive better outcomes for patients. And the elephant in the room is about how we keep things human. And this is what I wanted to speak about today, because this is the magic of medicine. Human intervention, we know, is critical to patients actually feeling better. And in recognition of how far we've come, I want to take us back in time to a past era, pre-COVID, where an idea that a machine could replace any part of the analysis of any eye care, investigation was completely remote. And what we had to worry about back then was really about patients printing out articles that they'd read online or telling us what they'd found on Dr. Google. And back then in 2017, so nearly 10 years ago, I was thinking about home monitoring of vision and putting some data in the patient's own hands. And I believed that potentially 50% of the patients in my cornea clinic could be seen remotely if we had the right data. And as well as lots of people in my department thinking I was mad, they also thought this was rude to suggest that this was the case. And going back in time, I used to work and live at this time in Bristol, which is in the west of England, and as well as being in Bristol, as well as having this beautiful bridge in Bristol, we also have a great eye hospital then, and it was fascinating to see how things change pre and post COVID. And when we think back to those times, and I think back to Bristol, patients really did have limited access to their own data. It was only the engineers who came in with their notes written from all of their different appointments they'd had in the past. And we spoke then about things like compliance. We didn't use the word adherence. Everything was very paternalistic in healthcare, and we certainly had no remote data. So the context of this talk is about how things have changed, and it's about the context is the increasing virtual clinics that are happening, especially in high throughput macular disease, and the asynchronous communications that we've built up since COVID. And I developed accurate home monitoring for visual function on the smartphone, and essentially figuring out remotely when does that patient need an OCT between pre-scheduled appointments. I naively used to think that we'd be able to automate everything with this technology if we had accurate measurements, that there was so much that we would be able to do, and I naively used to think this. But what I now realize is that remote monitoring, of vision, it's not a Fitbit. What we do in ophthalmology is very, very different to what the wearables and everything that we can experience outside of medicine. And I think even if we take, for example, Whoop just last week announced that they were going to make Whoop doctors who had access to all of this data to help contextualize it. And so for me, what's most important now in the technology that we're developing is the importance of a human in the loop and the importance of a patient being able to speak to somebody very quickly when there's a problem in their data. And so, for example, you can see here on the small graph on the right, you've got visual acuity data at the top, you've got distortion data at the bottom, and you can see there that when there's a change in that person's vision that I've marked with a lightning bolt, that's when the patient really needs a human in the loop. And that's my early learnings is that that's the bit that we don't want to try and automate with AI. So what do patients think of AI? Well, this has been explicitly studied in the macula already. And there's a study group in the Macular Society in the UK and with Prof. Foss out of Nottingham, who specifically asked patients what did they think, and these were patients who had various macular disease, and interestingly there was no association between their answers and their age or their gender or their level of education. But the patients were absolutely happy for an AI to look at their macular scan, provided that it was deemed accurate for the most part by the doctors, but also that it was quick. If it enabled a quicker decision, they were certainly happy with this, and also provided that there was a checking mechanism available. So this was quite unexpected. And there's also huge benefits. I mean, despite the provocative title that I've given, huge benefits of AI. There's increasing evidence, anecdotally, not yet in the literature, but anecdotally, that patients are opening up and asking questions that they would love to ask their doctor, but asking AI. And this is really interesting. And if we're completely honest, I think a lot of us have used an AI to ask questions, perhaps in the middle of the night, that we might not ask our own doctors face to face. And this is really changing the game. And when we think about AI and when we think about trust capital, because all of this is very much about trust, there are ways where AI, evidence is building, that we can increase trust capital. And that's when AI improves access to care. And that's also when it identifies deterioration earlier and when patients are empowered and they have reduced waiting times. But we all know in this room that there's huge opportunities as well to consume that trust capital. And this is what we need to be careful of. And really, I think it's also about labeling. So if a decision's being made by an algorithm, we should say to patients, this has been reviewed by an algorithm, this will be checked by a human or it won't be checked by a human. And this is the kind of thing that we can do really to increase trust. So we must drive efficiency. We must automate to make our services better. But when do patients need a human? Now, there are obvious examples of when we shouldn't be using AI. So for example, if there's unrepresented populations in a training data set, or perhaps whenever taking consent for surgery. And if we look at workflow, one of the questions I wanted us to ask ourselves, are we designing workflow when we're redesigning services? Are we designing for a human in the loop? And this is absolutely critical to keeping that human connection with our patients. And this is the key question that we're coming to. When does trust matter more than efficiency? A lot of the questions that patients ask us in clinic are not about them seeking information. A lot of them are existential questions where the patients really just need to have their hand held and be told that everything is going to be okay. They need to feel that the world is stopping for them and that there's a human, an experienced human there to answer their questions. And so I propose to you, are there new AIs to be developed beyond imaging and data analytics from EMRs? Are there new AIs to be developed where we can train prior to an appointment an AI to see a whole person, to understand what's that one question that they really want to ask in their appointment that they're waiting until that moment, the doorknob syndrome where they're waiting just until they're about to leave and say, oh, by the way, doctor, I have a question for you. And I'm sure the physicians on this call will recognize that. And so one of those projects, it could be something that we're working on at the moment is developing information, contextualizing information for patients. And so creating information in a way that patients can understand. We've got a big project just launching this for diabetes, and it's about taking standard information, personalizing it for the particular profile of that patient based on education, age, and how they want to receive that information. And so this is an invitation, certainly for anybody in the audience, whether you're a physician across the world or pharmaceutical, to get involved in an AI, which is going to, produce really personalized information for patients so that we can drive better adherence and better engagement in their care. So big uses of AI outside imaging. And I want to say thank you and leave you with that question. And really it speaks to the role that clinicians will take in the AI world. So thank you.
Thank you. That was great talk, Dr. Campbell. And don't leave us yet because we're gonna have the Q&A. So in the next after this next talk, so please come back and we'll discuss it. And thank you for putting those questions in the chat box. We'll get to them. We have some really great questions in that chat box, and we'll get to them at the end. Dr. Chan will be speaking on artificial intelligence education and curriculum lessons learned from ROP training.
Great. Thanks, Dr. Singh. And thanks to the organizers, Dr. Lang and Ferreira and Lim for having me here. So I'm just going to touch on, I love Dr. Campbell's talk about human in the loop, right? Because we'll sort of discuss around the educational sort of issues that we're facing with AI. Let's go to the next slide. Great. Here are my disclosures. Go ahead. Next slide. And just recognizing the group that I work with, I'm going to talk a little bit about some of the early education work that we've done, which really set us up now for what we're talking about regarding how can AI affect medical education and also train doctors better. So when we look back in time, we talked a lot about, I'm an ROP expert, so I worked a lot in this pediatric retina space, working with pediatric ophthalmologists, trying to understand what their perceptions were of artificial intelligence in the early years. It was no surprise that most felt that it was useful or would be useful or important in their clinical care of their patients. But I think that what was lacking, and I think we recognize this, is that most of us did not get a lot of experience or education in medical school or even during residency and fellowship training around the use of AI and specifically technology in a standardized way. So through the American Academy of Ophthalmology, some years ago with Michael Chang, we put together some papers around what do we have to think about, right? So what would go into an artificial intelligence curriculum? What are the important things to consider when we think about informatics and data and all the things that we've been talking about today? And fast forward, 5 or 6 years later, we're still trying to figure out how to integrate some of this stuff into at least our US-based graduate medical education. So also, things to consider are there are a number of organizations out there like the Collaborative Community on Ophthalmic Innovation who have done a lot of work. And, for us with the ROP, looking at sort of papers on some best practices and so forth on artificial intelligence. So here, I'm going to mention this paper here that also P. Campbell is going to talk a little bit later about the vascular severity score, where we started to think about plus disease, which is an important measure for diagnosis for ROP on more of a continuum of scale. And this kind of sets us up for the artificial intelligence question. What we have learned, though, is that you do need good telemedicine infrastructure to implement a good AI program, at least for ROP. But we've also used digital imaging extensively for the use of ROP education. So this is sort of a setup now for sort of how we're using AI to look at how we can train doctors better. So we published a number of papers, and some other groups have as well, on the use of imaging and a number of web-based ROP education interventions. And then now, since we have this vascular severity score, and through Gil Bittenbaum, we also have something called the P-score, which is more of a clinical tool to help us diagnose ROP better. So now we're undergoing a series of studies looking at how the VSS, so this AI-based vascular severity score, can potentially improve diagnostic competency for learners. So here's the study itself. So you have a pre-test to look at what the baseline is for each of these learners. You go through a series of images. You pick what your vascular severity, you pick your diagnosis, what you think the P-score should be, and so forth. And then you're given a series of interventions. One is just looking at a series of images with the P-score by itself. One is looking at a series of images with the vascular severity score by itself, and then a combination of the two. And currently, what we found, which is interesting, is that the VSS is actually more relevant than the P-score in terms of improving diagnostic competency. So, the big question is, how does AI potentially help us learn better and be better doctors and make a better diagnosis? And again, going back to Dr. Campbell's talk about the human in the loop, it's incredibly important for learners to understand the limitations and also the opportunities for the use of artificial intelligence and also technology in general. So we put together a group, this is technology, education, AI, and clinical informatics in healthcare, which is uh, a group of people that aren't just ophthalmologists or scientists. They're folks from the educational world, from the ACGME, also from the AMA, and other leaders who really think about how do we deliver education, how do we measure outcomes and success for our learners and also for our patients. So we had this over the past 2 days, and this is an ongoing effort over the next year. So let me just, next slide. There we go. Okay. So the big question is, how are we preparing ophthalmologists to integrate telemedicine and AI into their clinical practice? We still currently don't have formal curriculums across the board for ophthalmology education. And through the AAPO and the Academy and other organizations, we're working through that. I know Dan Ting sits on the Academy Task Force for AI. But of course, we think about other considerations around education, humanism, kind of how do we doctor the art of medicine? So also not just looking at precision medicine, but precision education. Can we use AI to make doctors better? And then in this study for the ROP work, what we're learning is that the AI does help learners. This is unpublished data at the moment, but then there are other very organized initiatives such as this educational program that I talked about that will sort of dig into this more and hopefully set curriculum for our learners in the future. So Dr. Singh, thanks again, and hopefully we have some time for discussion.
Yeah, thanks, Paul. That's great. Perfect. It really brings up a fantastic discussion, and we have some questions from the audience. We'll have our panelists join us. I think this first question is really, I think, timely for both a couple of our audience, our panelists from this morning, mainly for Tobias and for others that have worked in this space, and asking the question about how you integrate some of these AIs into EHR systems. Have you had any experience with that? You talked about exportation of data. That's always troublesome. You're dealing with this on a global scale, Tobias, and I think Manoj, you worked obviously in a couple different areas. Dr. Alam, you worked a couple different areas. Tell us a little bit about those challenges, what you've been able to do, what's truly locked down.
Who wants to start? Okay, I can
Yeah.
start. So, there are a lot of legal issues with integrating AI into EHR systems. So, one condition is, of course, everything needs to run locally. So you could not use like external servers where you transfer anything from your own EHR to the server and get a reply back, which is the most common usage of things like ChatGPT. Yeah, so that wouldn't work. If it's local, there are a lot of legal administrative issues actually to get this through. Yeah, so we have at MGB, we have a so-called AI zone where there are local servers which may be used even with EHR data, but to my best knowledge, this is not integrated in any front ends. Yeah, this is only for research purposes where people access backends of EHR systems, use that data, transfer to AI zone, get a reply back. But in the front ends, I'm not aware actually that the doctors themselves could use it.
Hmm. Dr. Alam, have you had experience you work with many different collaborators. How do you work between institutions and kind of working on that?
Yeah, so far our work has mostly been kind of collecting EHR data for vision language models across institutions. So I agree that I think there's not a good standardized method of actually doing that. I think, and also as Tobias mentioned, that there's a lot of admin and IT hurdles, and
Mhm.
each institution kind of have their own way of doing that thing. Some are more central, some are more department specific. So it's like more like the initiation takes a lot of time for any project that requires EHR. But they do have very important data, like text and image integration is really crucial right now. So I agree that there should be like a standardized method. Maybe we should all think about doing that, sitting in sessions like this.
Yeah,
Yeah,
that's
so Rishi, just want to comment because
yeah.
you know this more than anyone here on the line as a hospital administrator. But just for the audience, I mean, I sit in the same space, as chief innovation officer. So there are governance, there's governance within the hospital that to look at how best to use AI and adopt AI within the system. And I think that one of the things we have to sort of think through is also how do we learn from our radiology partners, because they've done a ton of work in this space, right? And are actively using AI or sort of some form of it. But the data integration piece, that I think is what everybody's talking about here, and that's super complicated. And then if you look at how to actually work with international partners, it gets even more complicated, right? Because then you're thinking about international laws and so forth.
Mhm. Yeah, and I think that that's very important to understand kind of like the limitations and all this. I think people
Right.
think, okay, Claude is out there, I'll just stick my, my data
Yeah.
in Claude. That should not be the answer from this conversation. I think that's a very important point. Paul, you brought up education. It's so key, right? And you obviously did a fantastic residency program. How are you starting the conversation with your residents, fellows, if at all,
Yeah.
about being AI enabled?
Yeah, so one, we started tracks, and I think a lot of programs are doing this, where they have the data scientists or they have the CS folks or the people who are clinician experts in AI and technology, creating more structure around when they come into residency, a set curriculum, and then finishing with a concentration to a certain extent. And I think that's kind of where we're going. So this is the whole idea of like personalized education, right? Like how do we, get people excited about things they're interested in? But I also think we have to look externally, like Minhaj, right? Like, you're not within ophthalmology specifically, but partnering with the folks that are outside who are expert in this, and that's what we do. We partner. So working through a curriculum with your medical education experts in your system.
Yeah. I don't know if Dan is still on, but I'd love to hear the international kind of experience with that
That's right.
and teaching that. Dan, how are you enabling your residents, fellows, workforce with AI?
Yeah, well, thanks, Rishi. Can you guys see me?
Yes.
I was just told
Yeah.
that my camera is not on.
Yes, we can see you.
Okay, all right, okay, now it's on. No, yeah. So, the I mean, in terms of the teaching, I think we actually if we actually go with a couple of stakeholders, the engagement. So basically, it goes from the clinicians, allied health professionals, the staff, administrators. I think depending on what specialties that you're in, um, the scope of the AI teaching will be different. I think the basic of the AI, the curriculum, it should be the same, but the basic it simply means that what is AI, what is machine learning, what is deep learning. But in order to teach the basic, the generative AI skill sets, I wouldn't even bother teaching them about what deep learning, machine learning is. I think using a very um, simple prompt to help them with their workflow, I think that alone could already increase their efficiency by 25 to 30%. I think I mean, that is something that I think is highly useful. In terms of the Gen AI engines, I think it's very important, like what I show in the slides, to uh, let them know which one are the open source and which ones are the closed source. I think
Yeah.
the closed source model is the one that's commercially available. I think that's something that people are often are using, but I think the data safety and the sovereignty is something that we have to teach them how to use it properly. Yeah.
Yeah, great. And just to finish up with the kind of on the personalization, we've talked about personalization. of curriculum. Stephanie, when you spoke about the patient's personalization, how are you managing that? I mean, obviously in this application that OPCO is involved in, there's a lot of variability. What is kind of the mechanism for personalization in that large model?
Yeah, I see your technology as having two halves. There's personalization in monitoring data and looking for changes in data. And so making sure that our algorithms are looking for changes even at the eye level, because we know that some patients have more variability in functional and structural measures in one eye than the other, for example. So assuming, so not just personalizing at the individual level, but the eye level, that's really important, because then if a measurement is moving out of what's expected, you can then flag it on a personalized level for that patient, even with basic statistics. And then the personalization on the education level. So what I learned early on was that home monitoring, it doesn't even matter if the patient isn't educated as to why are we doing this. How does this match to it? How does this drive adherence, for example, in a treatment plan? Does the patient even understand the treatment plan? Do they understand what we're monitoring for? And why, if they have symptoms, do they need to accelerate a visit, for example, back to the clinic quickly? So the personalization in the education is critical, and that's something we've got a huge focus on at the moment. We've got a new project in diabetes, but in AMD, the focus has very much been on what phase of the disease does this person have. Let's give them disease stage specific information. What services are available to them locally? So we've got data, on their zip code or their postcode, for example. So what can we drive? What information can we provide them that's local there? And so there's a lot of, in terms of support services. So the way that we're looking at the personalization is saying, look, well, if a doctor had 30 minutes to sit down with a patient and have a cup of tea or coffee, what's the kind of things that we'd say? Well, how would we personalize that? And what can we do pre-appointments, post-appointment? Most effectively. So it's really interesting. I think, yes, we need to standardize with AI, but I think the personalization opportunities beyond just the treatment plan are really, really exciting.
Yeah, that's great. Well, thank you all for a wonderful discussion. Really appreciate your participation. We're going to go on to the next session, which will be by my co-moderator. See the slides come up in
Thanks,
just.
everyone. Take care.
Thank you. And I'm going to turn over to Dr. Daniela Ferrara. She's lead us to session 2. Daniela?
Thank you so much, Richie. So it's my pleasure to start session number 2. And I would like to invite to the virtual podium my dear friend and colleague, Dr. Amita Domalpalli from University of Wisconsin-Madison. She's going to be discussing pre-screening models for diabetic retinopathy in clinical trials. Amita, the floor is yours.
Thank you. Thank you, Daniela and organizers. This is such a wonderful meeting. And I'll be talking about pre-screening models for diabetic retinopathy. And here are my disclosures. We all know eligibility in clinical trials is such a big hurdle. There are screen failures. It's an elaborate process. It's kind of inefficient because images come, you recognize eligible patients in the clinic, submit to the reading center, double read adjudication takes 3 to 5 days, and then, eligible, ineligible. So what if we changed that paradigm and brought the reading center into the hands of the clinicians by bringing cloud-based AI systems with real-time reporting that can help speed up this process? We all know diabetic retinopathy severity scale, which is the FDA-approved way of assessing DR, is complex, it's elaborate, and most clinical trials want to use the 47 level as a cutoff for enrollment. The screening DRs, the population screening DRs, use the 20 to 35, that level as the cutoff, which is very different from what clinical trials use. And clinical trial pre-screenings generally have a 60 to 80% screen fail rate based on ETDRS levels. So our question was, can AI pre-screen retinal images, and can it eliminate clearly ineligible patients? Ultra-wide field color is commonly used for diabetic retinopathy documentation, although clinical trials do use 7 field. So if you had a lot of standard of care images that are used in the clinic or for pre-screening, we could deploy them as a mode of detecting ETDRS levels. But these ultrawide fields do create a challenge for AI. One, they are extensive, they're really big. The lesions are small and lost at scale because the ERMA and microaneurysms are tiny. There's no pixel level annotations for ETDRS level. It is just happens in the grader's head and they give a level. And it's a subjective ordinal scale. Yes, it is subjective, but also it is not a continuous scale. It jumps from 35 to 43 to 47 and all those numbers. So it's almost like categorical. So here's an eye. Left is not eligible, right is eligible, but it's difficult to know what's what because of the small image, small lesion, big image problem. And that's depicted here. So this is an image of an ultrawide field with diabetic retinopathy. Those are the kind of lesions that we are trying to detect to determine eligibility. And when when the graders look at these images, they look like this. But when they're fed to the AI, they're downsized, resolution is lost, and features are lost. So our problem is that when these images are downsized for AI, whether it's 224, 224, 512, or 768, the resolution is insufficient for lesion detection. So the thought was, what if we do patches of these, maintain the resolution, and then feed them to the AI instead of the entire image? So this model used this patch-based attention, multiple instance learning. So the image was cropped, lashes were cut off, 7-field region was identified, and then the patches were fed to the model to develop this ETDRS classification. So this is the data set. And again, the cutoffs here are whether the patient is not eligible or eligible based on that moderately severe NPDR, which is level 47. And there was a training data set and an independent test set. One of the other things that the model had to take care of extensively was to reduce the false negatives to a minimum. And why is that? That's because when the AI says the patient is not eligible, the patient does not see the light of the day. So they're removed from the clinical trial process, whereas eligible patients come to the reading center for a second level screening. So you don't want to make mistakes and lose these potentially eligible patients by the AI miscalling them, with the price of overcalling on this side because the reading center will take care of them. So that is another specificity that we had to put in. So how does this work in a workflow? We had 6 to 58 patients in a pre-screening process. When submitted to the reading center by themselves, 63% of them were called ineligible by the reading center. So there's no AI involved here, traditional method. But when we brought in the AI into the same data set, 235 were excluded. So the reading center did not have to review these. So at site level itself. So it's not the screen fail rate, but how many the AI is able to prevent from reading center submission. So 36% reduction in reading center submission, which means improvement in efficiency, time, and cost and burden for the sites. So there's a 6% false negative rate. That's the one that I was talking about. We monitor that very carefully because we don't want to lose anybody. So a 36% reduction in submissions means faster enrollment, lower cost, and less burden on patients and sites without sacrificing safety. So it doesn't replace the reading center, but the reading center experts are preserved for the most important cases. Of course, we do have to do a prospective validation in an active DR study. Retrospective, always the AI performs so well. So this is kind of the workflow we've implemented where patient is potentially examined, an ultra-wide field image is submitted and to the cloud-based environment, and a report is generated. And the report gives the PI exactly well below ETDRS level 47, and that's what the model does. This is not an autonomous diagnostic system. It's a triage. It's a pre-screening tool. Final decision always remains with a human expert. And that's our team. And thank you so much for your attention.
Thank you so much, Amita. Very, very interesting topic. As the next speaker, I'm going to invite Dr. Maida Hadzamitovic from Duke University, and she's going to speak about the comparative large language models evaluation for AMD recognition using OCT images. The floor is yours, Maida.
Thank you so much, Daniela. Thank you so very much for inviting me to this amazing webinar and everything that you guys are doing. I think it's so relevant and important in this very time. So I'm going to be talking about, I would like to go back to the previous slide, please. I cannot advance my slides, but I'm going to be talking about a comparative large language models evaluation for identification and recognition of some image biomarkers that are associated with age-related macular degeneration, mostly drusen and choroidal neovascular membrane. This work has been supported by the NIH R22 grant. Can you please go further? Next slide, please. So in general, traditional deep learning methods for any type of the classification and prediction, they face several problems. And one is a limited generalizability. What does that mean? Many models are trained on a single modality data set, whether that's the OCT, whether that's the color fundus photo or other. There is no consensus, and they could not be generalized to multimodal imaging tasks. There is also data set bias. Commonly used data sets that we are using are associated with old clinical trials, AREDS, fundus photos. Then those usually overrepresent certain demographics, in this case Caucasian, and then very frequently underrepresent staging of the disease. Overfitting is always a problem, and it has been with the AI. Many models perform beautifully on the curated data set. We sort of pick and choose what we use them for, but then when we put them in the real world setting, they don't do as good. Next slide, please. So new stuff coming along and our way is amazing. So large language models can reason across modalities and domains. We have the foundation models that have been pre-trained on a large text corpora from the internet, and they can be prompted directly for medical tasks without any other fine-tuning. Large language models, on the other hand, could also be coupled with the agentic framework that can plan, retrieve external knowledge, and very importantly, can call API for tool use, which actually allows us to actually fine-tune what we need and then can evaluate the response quality and guide the language models to actually go in the direction that we need them to go to. Can I have further, please? Next slide. So what we did, this is just actually one fragment of the study that we're doing. The bigger story is actually under review, and I hope that the manuscript is going to come out soon. But we actually chose the open source OCT data set, and we pulled out 70 representations of the choroidal neovascular membranes and 70 presentation of different type of drusen that was randomly selected so that we avoid the bias as much as we can. In this case, we included non-reasoning large language models and also reasoning augmented large language models. For this particular talk, this is actually a limited large language model representation. In the manuscript, we actually are working with some novel large language models as well, and then actually we implemented them. I don't want to go into detail when it comes to the implementation, but I just want to tell you that the interface cost was actually very acceptable. As a matter of fact, it was minimal. Can we go further? Thank you. So we did a little bit differently. We wanted to have a human in the loop, and we wanted to have an LLM as a supervisor, evaluator. And then also we wanted to have a number of LLMs to be diagnosers, that actually they would be fed information, but also fed the prompts. We had the grading rubric. And then actually first, we wanted to choose out of the all LLMs that we were using, what LLM would be the best example for the evaluator. That would be the one with the best accuracy. Then we would compare that one to the human retina specialist as an evaluator. And that way we actually came up to a conclusion that Gemini 2.5 was the best one. So in brief, the The LLM evaluators were prompted to grade each diagnoser output against 4 rubrics. One was the accuracy, the other one was the feature and the differential diagnosis and clarity. Next slide, please. So this is just one example, and it's a very good example of the Gemini 2.5 Flash, how actually diagnosed beautifully a wet AMD out of this image. And what we also wanted to see is the thinking process. So we wanted actually to find out what are the key features that actually the model was looking into and using for the setup of the diagnosis. Next slide, please. So we went further. Now here we are comparing evaluators. We are comparing different large language models to uptake the role of the evaluator. And then we were comparing that to one retina specialist. So this is actually human versus LLM evaluator agreement. We had 4 different LLM evaluator models that were tested and benchmarked against human evaluator within a very small data set in this case. And then the data points represented the average score assignments. And we can see that actually there is a great agreement between the human evaluator and the, in this case, Gemini 2.5. Can we go next slide, please? These are, again, agreements. These are agreements between the Gemini 2.5 and 2 extra retina specialists. You can see that actually the agreement is close to perfect. We can go further, please. These are some of the results. You can actually see that automated grading and ranking was presented here in a large scale. We had large language diagnosis score distribution across 140 images that were evaluated by the Gemini. And then also, besides being a great evaluator, Gemini 2.5 was the best diagnoser as well. And all models had high variance in terms of their performance. The best diagnosis for each OCT scan was present in the right hand of the image, and the score was pretty high at 5.5. Next slide, please. So this is a little bit more nitty-gritty. These are actually newer LLMs that we incorporated. So you can see that the newer models perform better. This is actually performance over the diagnostic accuracy, features, imaging features, differential diagnosis, and the clarity. And actually, in this case, Gemini 2.5 was outperformed. More about that is in the manuscript, and I hope that you will be able to see it soon. Can we go to the next slide, please? So these are just a couple of examples. This is a case where the LLM misclassifies the fibrovascular PED because the focus of these 2 LLMs was actually in the totally different area. You can see on the right hand that one was the macular hole, the other one was vitreomacular traction syndrome. There is the reasoning why they're doing it that way, but the final output is wrong. And can we go to the next slide, please? This is even more significant. This is one of the best diagnosers and evaluators. This was Gemini 2.5 Flash. Actually, this fibrovascular tissue was called choroidal melanoma. This is in the now, in this time, very dangerous because patients are using large language models for their diagnosis. And you can actually also see the reasoning. So the LLM was gathering a lot of information for the internet, including the dome-shaped irregular contour, subretinal fluid, and actually that's how it came up to the diagnosis of choroidal melanoma, which was fairly wrong. Last slide, please. So in the conclusion, large language models evaluators demonstrated a high level of agreement with the human evaluator in supervising the quality of the AMD diagnosis, drusen and choroidal neovascular membrane. The proposed workflow showed the potential that the LLM's powered automation can be a great thing for diagnostic quality, but actually human in the loop is really required for the evaluation. And that would be actually the final food for thought. And I love that a lot of talks that I've heard today are still talking about the importance of human supervision on all of these new advancements that are coming our way. So thank you. We can go to the last slide, which is just a thank you note. I'm very grateful for your attention and happy to participate in the discussion.
Maida, thank you so much. Great topic, and I'm looking forward to the panel discussion to ask you more questions about your experiments. Thank you. Next, it's my pleasure to invite to the virtual podium Stefan Smith-Valkenburg from University of Utah. Stefan is going to discuss the prediction of visual function using OCT in patients with geographic atrophy. Stefan, the floor is yours.
Yeah, thank you so much, Daniela. I would like to thank the organizers for the invitation to join this innovative Ophthalmic AI Summit 2026. And on behalf of the Oaks Derby and Gale investigators, and on behalf of all my co-authors, I'm pleased to present functional OCT in geographic atrophy today. Let's see, next slide, please. These are my disclosures relevant to the talk. Is that the content that I'm going to present is partially based on contracted research to Apellis. Next slide. Most well-established functional tests, including best-corrected visual acuity, show only little correlation with GA manifestation and growth, as demonstrated by the CHROMA and SPECTRI data, these two large independent phase 3 studies within large GA cohorts. It remains an unmet need to identify functional measures that are able to track GA progression more effectively. Next slide, please. Microperimetry appears particularly promising to effectively bridge structure and function. Of note, in CHROMA and SPECTRI, MP was the only functional test that correlated with GA growth. Next slide, please. However, microperimetry has several limitations, and these include limited access and lengthy testing for patients with poor fixation. And importantly, even when we're testing with this extensive time-consuming 68 stimuli grid, as shown here on the left, this actually represents a sparse pattern, as it can obviously miss functional changes in between neighboring measurement points. And if you consider the typical rate of GA growth of about 100 to 300 microns per year, it becomes evident that it would take about 2 years for GA to spread from one test stimulus to the next neighboring test point. Next slide, please. Previously, our group introduced a novel and innovative solution called inferred sensitivity. Using AI, microperimetry and volumetric OCT imaging data is trained and then used to estimate retinal sensitivity at each en face pixel. As shown here on the right, this yields a high-density sensitivity map, actually similar to an en face OCT thickness map. Next slide, please. Similar models have been developed to infer retinal sensitivity for other retinal diseases, including Stargardt disease, neovascular AMD, macular telangiectasia, or central serous retinopathy. Next slide. And this approach has now been further developed into a tool called functional OCT, or OCTF, in partnership with Apellis, using the imaging and extensive microperimetry data from both sham and treated eyes from the pegcetacoplan clinical trials. Next slide. For the development, AI was first trained on untreated fellow eyes from Oaks and then tested on the full Oaks dataset and then on Derby. For Derby, no MP data acquisition was included, so the model provided functional insights even when actual functional test had not been employed initially. Next slide. Training used layer thicknesses and intensities derived through the Great Reading Center segmentation algorithm, spatially correlating to the decibel value at each microperimetry point, and evaluating the model performance, that is comparing the estimated retinal sensitivities by the model to the actual MP values as tested. A correlation with through sensitivities with a mean absolute error of approximately 4 decibel was seen. Next. Here on the right, we see the biological plausibility. The feature importance is displayed, and as you can see, different photoreceptor OCT bands are the most important factors to predict retinal sensitivity, while other layers such as RPE or drusen complex choroid contribute much less to the model. Next slide. The mean absolute error of 4 decibels with OCTF, as shown previously, is very much comparable with similar errors that have been reported for inferred sensitivity models in other diseases. Of note, and this is shown here on the far right, the errors of inferred sensitivity are also in the range of actual testing. Next slide, please. OCTF has been further validated externally, and this is now an outside data set, so outside any pegcetacoplan study data, using real OCT and microperimetry data from a cohort of 39 patients from the directional spread and geographic atrophy natural history study that had been performed at the University of Bonn, Germany. And here we can see that the OCTF model that was trained on the Oaks Fellow A data showed strong performance when comparing real and inferred sensitivity values. Next slide. And this slide is an example of one case and shows actually the power of OCTF. It's from a sham patients in the Derby trial. So no actual microperimetry testing was done, and you can see the absolute scotoma shown by dark colors progressing from baseline to month 4. Next slide. This is another example from the Oaks trial. Here showing multimodal imaging findings on the left in a subject with GA, and on the right, the OCTF functional map is shown. And note that even a very small atrophic satellite just below temple to the fovea is detected by the model that correlates to a small atrophic patch by the multimodal imaging. And next slide, this is confirmed here in another example where we also have the large patch of atrophy with a deep scotoma and also a small atrophic satellite. So next slide, looking at the overall data, so applying OCTF to pooled Oaks and Derby data, the results reveal a statistically significant difference versus sham in retinal sensitivity loss over the 24-month study period, and there's a difference to sham of 47 and 36% in the monthly and every other month's treated group respectively. Next slide. We know that from the clinical trials, from the previous presented data, that pegcetacoplan was more effective in non-subfoveal lesions in Oaks and Derby. And similar effects are shown here for OCTF. So the difference to sham and preservation of retinal sensitivity in subfoveal lesions here shown with 44 and 36% in every month and every other month treated eyes is pronounced, but overall less. Show next slide. To the non-subfoveal lesions, we can see that the sensitivity was better preserved in these non-subfoveal lesions. And next slide, when we look at more follow-up data, can we have the next slide, please? Can you go one back? I think we skipped one. No, yeah, that's the 4-year data in the Gale data, which shows preservation of the effects. And next slide, this is a final slide with the data, which shows the further post-hoc analysis. It suggests that OCTF modeling can also predict the rate of future GA progression. So the graph shows the progression of GA over time among the 4 subgroups. And these subgroups are defined by the inferred sensitivity values at baseline. So in the pale blue group that has relatively good function in the border zone at baseline, the further GA progression is slower as compared to the other 3 groups, which show a much more rapid progression over time. Next slide. In summary, OCTF is a novel AI algorithm that bridges structure and function. Hereby, AI models are trained on data from large GA cohorts and then reliable infer microperimetry sensitivities from OCT images. Use of OCTF reveals the preservation of inferred sensitivity with pegcetacoplan treatment, not only in the Oaks, where MP data was collected, but also independently in Derby. OCTF predicts patients at risk for faster functional loss based on junctional zone sensitivity, potential as a functional surrogate outcome in GA trials, especially in reducing trial burden and probing localized sensitivity loss. Thank you very much, and I'm happy to take any questions later.
Thank you so much, Stefan. Very interesting research. Next, is my honor to invite to the virtual podium Professor Ursula Smith-Efford from Medical University of Vienna. Professor Smith-Efford's work has been revolutionizing clinical trials in geographic atrophy and continues to do so. Today she's going to discuss about the assessment of function loss in geographic atrophy, also focused on retinal sensitivity analysis. Ursula, the floor is yours.
Thank you for the introduction. So, how can we best assess functional loss in geographic atrophy? And retinal sensitivity has been mentioned multiple times, and I think that we can say that there is a major consensus that retinal sensitivity is the opportunity to do this in the most constructive manner. Next, please. Next, please. So, disclosures. Next, please. There are three different principles for pattern designs in microperimetry. There's the standard grid covering the entire macula with usually 68 equidistant points, ideal to assess overall macular function, but no reference to underlying morphological features. Many points disappear in intact or lost function. Next, please. A circumferential grid referred to as an onion ring, where classically 60 test points are placed all around the lesion borders with the aim to capture any expansion of the lesion, which is the area of RPE loss, ignoring the fact that disease activity is not distributed evenly around the GA borders. Next, please. And there's a feature-targeted grid registered to the morphological areas of disease activity, such as the EZ loss area in green. Such a precise co-registration is best done in an automated, therefore standardized manner, excluding subjective user variability, applying the lowest test point number needed, and focusing on the largest level of loss, which is transition from early photoreceptor disease, reflected as EZ thinning, and conversion to RPE loss, which represents absolute scotoma. The points of interest are fovea, pairing of predicting conversion lines, and particularly the EZ loss boundary. Next, please. Just look on the right side, because it shows you the dynamics of morphological change and according to that functional loss. It is based, what we test, on evidence obtained from 40,000 microperimetry locations monitored over time in a large GA trial where areas with EZ loss demonstrate progressive sensitivity loss from a mean of 10 decibel. This is the mean of relative scotoma you would currently see in the area of EZ loss, to 0 decibel as soon as the EZ has converted to RPE loss. In those three lines, you see different speeds on the left side, either 24 months or 12 months, or even earlier, dependent on the speed of disease. Dependent on the speed of this morphological conversion, predicted by the baseline EZ-RPE ratio, absolute scotoma in blue, which is RPE loss, will wipe out the green relative scotoma, which is EZ loss. Next, please. We also know by looking and calculating the morphological transition probabilities that conversion will happen only in 1% from intact retina to RPE loss, whereas it happens at a chance of as high as 23% in areas of pre-existing EZ loss towards RPE. Next, the base for robustness of this analysis obviously depends on the precision of the segmentation tool. This is extremely high with the GA Navigator, which we developed, a dice score at 0.99, highest precision for RPE and EZ measurement. You may have seen the comparison of different EZ algorithms by Kukras at the imaging meeting at ARVO just lately. Next, please. Having provided this evidence, we can now proceed to provide optimal functional endpoints for GA trials and clinical routine, compare different patterns in terms of efficiency and signal strength, assess rate of detection, as well as the number of test points, and finally, time needed. Next, please. Here is the first step: detection of morphological progression, morphological conversion. We processed the data from untreated fellow eyes of Oaks and Derby, performed an OCT-based segmentation of RPE and EZ loss using the RetinSight GA Monitor 2.0. Next, please. The detection of morphological conversion was targeting the specific distribution pattern of test points of the 3 classic patterns as described in the literature, with an endpoint at 24 months. So this slide visualizes the distribution of these sensor points for the targeted. It's the upper line, the circumferential, the medium line, and the standard grid. And it's changed over time. Obviously, the principle is that you keep the test points where they are and see how the morphological wave change is going like flooding over it. Next, please. We found that the detection rate of conversion varied significantly between grids, with the highest detection rate reached with AI-guided targeting in red, less with a circumferential grid in green, and least with a standard grid in blue. For the EZ conversion towards RPE loss, the rates were 34 versus 27 versus 17%. For general conversion, i.e. any transition, the rates were 48 to 44 to as little as 27 for the standard grid. Not surprising that the use of standard grids in clinical trials has so far been really underwhelming. Next. In a second step, morphology can be correlated with corresponding retinal sensitivity values based on structure-function correlation using a machine learning model pairing OCT scans and microperimetry values in a pointwise manner. Such a model provides dense sensitivity maps from the underlying OCT imaging. Next, please. Our structure-function correlation model was applied to the same scan set. The 3 pattern style locations were identified for prediction of sensitivity change over 24 months, and the efficiency of functional testing was calculated. Next, please. Regarding retinal function assessment, the targeted pattern detected more retinal sensitivity loss with less test points. The raw change for all points was 2.5, 3.2 to 3.4 for the targeted grid. The raw change for outside loss was 2.7, 3.4, and 3.8 in favor of the targeted grid. Keep in mind that this is an all-comer cohort without even selecting for active disease. Next, please. The last step provides a scoring for optimal selection of the most promising point locations, which we may call candidate points. Next. That means that a morphology-based score was calculated for each targeted point, considering multiple influences of relevance, such as distance to the RPE loss boundary, focality surrounding EZ loss area, for selecting the most efficient candidate points for a truly targeted, most efficient, short-duration future testing. According to the FDA's suggestion of using 5 pre-specified points showing at least 7 decibels of loss, we searched for the availability of such candidate points in each grid. The targeted grid was most successful with the highest achievement in the targeted grid for raw change and efficacy scores. Next, please. So in conclusion, we were able to design an advanced framework to simulate different microperimetry grids on the large data sets. So the microperimetry grids were taken from the literature without any bias as they were described in the literature, and then the points were set on the OCT data that were true patient data. The targeted grid was superior in respect to identifying morphological conversion from EZ loss to RPE loss, and able to predict functional loss most efficiently. For the first time, this framework identifies the most relevant subset of points to be tested. So this is not a model, but this is a true testing in the areas that are changing most in terms of the underlying morphology, but the measurement is performed in each patient individually, with the few test points that I showed you were necessary and placed exactly where relevant. A reduction in test duration is achieved, which is substantial. Higher reliability in patients with GA than conventional microperimetry was achieved, and a robust base for regulatory approval of new drugs in clinical trials, which has been such a dilemma in the current true real world. So targeted microperimetry, a targeted grid provides realistic functional values and not just modeling, but based on a clear morphological analysis. Next, please. We thank all our partners that contributed to this, and I thank you for your interest.
Thank you so much, Ursula. This is such an impactful line of work, and your line of research for the last decade has paved the way to bring to all those advantages. So thank you so much, and thank you for being here.
My pleasure.
Now it's my great pleasure to invite to the virtual podium my dear friend and colleague, Dr. Christina Rabe from Genentech, whose work has also been quite impactful for several recent clinical trials. Dr. Rabe is going to discuss prognostic AI models for geographic atrophy and their application in clinical trials. Christina?
Yeah, thank you so much for the introduction. And I'm really excited to be here today and share some of our work. And as you might have guessed from my position, I'm the biostats ophthalmology head at Genentech. I will focus a little more on the statistical perspectives of how we can use these AI models in clinical trials. Okay, next, please. Thank you. So yeah, let's dive right into it. I was assuming you all know what geographic atrophy is, and in most of our clinical trials, the primary endpoint is still like an anatomical endpoint. So we evaluate treatment effects by looking at the lesion growth over time. Next. Next, please. Thanks. And while this is a very well-behaved endpoint in that it's not very noisy when you look at individual patients, pictured here on the right, some examples, there's quite some between-patient variability on how fast their lesions actually grow. And so experts have identified many features that are associated with the growth rate, for example, whether the lesion is uni or multifocal. But generally, this is not a very easy task for an expert to give a predicted growth rate. Next. So we built many different prognostic models using different sets of features and combining them. That also included models using many new derived features from images, for example, to better describe the shape of a lesion. And then in contrast to all these feature-based and more interpretable models, we also fed the images directly into an AI deep learning model to see how well we can predict the lesion growth directly from the image. Next. And so all these models were developed and validated initially on our large pool of data that we collected as part of our lampalizumab program, multiple studies. And initially, we were a bit surprised by the results. So we saw that the deep learning model that just uses the image directly as an input outperformed all the other models that were based on known and new derived features. So you can see here on the right, the model explains about half of the observed variability. So that's an R squared here of 0.48, which you see here the correlation between the predicted and the observed growth rates in our holdout data set. Yeah, but maybe this isn't so surprising given that it's an imaging endpoint, not very noisy, and there's so much information in an image that is really hard to quantify and describe to a model as an input. We are probably, as humans, not very good in capturing all that information and describing this, and this is where like a deep learning model can really learn that as long as we have large data to train it. Next. And this slide just gives a little bit more detail on the data that was used and shows further validation of the model in two other independent data sets that were not used for training. And you see we can replicate the great performance of this model. But now, yeah, let's talk a little bit more like how we actually use these models in clinical trials. Next. So in a trial, we compare the growth rates between the treatment arm and the control arm. And the treatment effects that we consider meaningful can appear quite small compared to the between patient variability. So that means it's not very easy to detect with high confidence. So what are ways to reduce this variability? Next slide. Next. So the first thing a lot of people suggest when we talk about the prognostic model is to use the prognostic score for stratified randomization. And what that means, next slide, is that we need to split it into categories. And then within those buckets, we randomize the treatment arms, and this helps to balance treatment assignments within those strata. It's then also used in the analysis. So we would include those strata as a covariate in our model. And you can see this explains some of the outcome variability, which means we gain precision in our treatment effect estimate. And the way you can think about this is within each strata, there is less variability or more similar patients, so it's easier to see the treatment effect. So however, given that our growth rate is continuous and our endpoint is continuous, this is not the optimal way to use this information. So how we like to use this information is for covariate adjustment when we run our model to estimate the treatment effect. So this leaves the score continuous. Oh, so I just lost my screen. I'm sorry. And really uses this information more efficiently. So you achieve the same goals that you try to achieve with stratified randomization, but more efficiently. And the way to think about this is that now the treatment effect is represented here by those two lines. And what matters is the variability around those two lines, one for each treatment arm. And if you have a strong prognostic factor, meaning a high correlation like here, this approach will make your treatment effect estimate much more precise. And so covariate adjustment would also correct for any imbalances observed for this prognostic factor. And you can think about this as rotating this plot. So that's squeezing the points together around these lines, which reduces the variability. And so from the left to the right, basically. And what's also important to mention is that this is a very rigorous approach. So there's also a recent FDA guidance document that really encourages the use of prognostic factors and scores for covariate adjustment in clinical trials. So now you might be wondering whether we can quantify this benefit. And if you have a prognostic model and you would like to estimate the expected benefit in a future trial, this can be actually estimated from the squared correlation. And we like to express the benefit in terms of effective sample size increase. And so this is a bit simplified here. There are some assumptions, and we have different formulas to estimate that's using different assumptions. But remember, our GA model that I introduced had like an R squared around 50% or 48%. So if we translate that into gain in precision, if we translate that into effective sample size increase, this means we basically would be running a 90% larger trial compared to using an unadjusted analysis. So this is very impressive. So you gain basically almost like double the sample size by using this adjusted analysis as if you were running a trial twice the size. So I also quickly wanted to mention another use case that people often propose, and that is enrichment. Enrichment means that we exclude patients based on their prognostic scores. So for example, we might think that it's a good idea to exclude maybe slower progressors. However, whether that is beneficial over covariate adjustment really depends on a lot of assumptions on our treatment effect and the variability, and you might not always increase trial efficiency. So on the left, for example, with the constant absolute treatment effect and similar variability around these lines, meaning that slow and fast progressors have a similar absolute treatment effect, you might not gain much by enriching compared to using covariate adjustment. And in contrast, because you're excluding patients, it takes longer to recruit. it's also a higher regulatory bar. So in those cases, it wouldn't really you wouldn't really gain much. Also, we don't always know if patients the treatment works better in patients with faster progression. Often people also think that maybe earlier treatment could lead to larger effects. So this might also not always hold true. Okay, so then in summary, I would advocate, specifically here in GA, for using prognostic models for covert adjustment as one of the most rigorous and efficient ways to leverage prognostic information. And as long as you don't reduce the sample size, there are virtually no assumptions. Stratification is, of course, a valid approach, but might not be worth implementing with complex models when covert adjustment can achieve those goals more efficiently. And then the benefit of enrichment really depends on the assumptions and should be pressure tested. And then the last bullet point we didn't really get time to talk about, but I also hear people often nowadays proposing using it as a control arm and replacing the control arm completely. And I just wanted to emphasize that that comes with even more strong assumptions and often non-verifiable assumptions. And with that, I wanted to give you some references here, and importantly also acknowledge all my colleagues at Genentech and co-authors here. And thank you for listening.
Christina, thank you so much. Amazing work. It's my pleasure to invite the last speaker for this session, my dear friend and colleague, Dr. Nadia Wahid from Tufts University in Ocular Therapeutics. She's going to bring it all home, and it's going to discuss how AI and retinal imaging innovation can help us with a better trial design, conduct, and analysis. Nadia?
Thank you so much, Daniela. And here are my disclosures. None of these are relevant to what I'm going to be talking about today. I think for me, just like Daniela said over here, as someone who runs clinical trials, one of the important questions that we deal with is how can we use all of these innovations in AI that you've heard from all of my colleagues today and use those to increase efficiency and the chances of finding the correct answer, whatever that may be, and therefore your ability to conduct a successful clinical trial. And that's one of the things that I will be focusing on. I do want to say that this is kind of putting together a lot of different stuff, and much of the important work on this actually has been done by my here we go. By my very valued colleague, who's the moderator over here, colleague at Tufts, and then currently Chief Medical Officer at Topcon, Dr. Daniela Ferrara, who led the Ophthalmic Personalized Medicine Unit at Roche Genentech that did incredibly valuable work and output on some of this. And then again, my friend and colleague, Dr. Saroj and Dr. Jamil, who have also assisted in this presentation. So as you know, with the advent of AI, there's been a global interest across the field of medicine and healthcare, and ophthalmology is unique because a lot of the imaging modalities that we have, whether those be fundus photographs or OCT scans, really capture cellular level or vascular level detail in patients. And so we have a rich, in a non-invasive way, and so we have a richness of data that you would traditionally get, for example, in radiology or in pathology, but all of this is done in live patients and in non-invasive manners. AI offers a unique opportunity to mine these data for patterns that may be valuable in clinical practice and therefore may be important for us in clinical trials. And then the second hat, why do clinical trials need transformation? Well, we all know that randomized controlled trials are the gold standard, but there are significant challenges with RCTs, and two big challenges: cost and duration. So, and to some extent these are correlated, but those are the two big challenges that we face when we pursue a traditional development pathway. There are multiple years, sometimes up to a decade, and in ophthalmology we're lucky because that is not as long as it is, for example, in oncology or in internal medicine. Sometimes it can take, a decade from when a molecule is first discovered to when the phase 3 trials are done, longer. And this becomes incredibly costly per patient costs in the US. For example, just in phase 3 clinical trial screens is more than $25,000 per patient. So there's an enormous cost to development of medicines that comes when we use the traditional approach. And of course, all of this is passed on down to us as a society. So societally as well, I think it really benefits us to reduce the cost of conducting clinical trials, as well as accelerate how soon you can get some of these medications out to patients. So the idea is to kind of try to accelerate all of this and compress this into a much shorter time frame using AI and machine learning modalities. And some of the advantages, of course, of that are, the cost reduction, getting these medications to patients safer. And of course, if you put on a drug development hat, every year that you cut in the development phase and are able to commercialize a medication, the better you're able to do. And so it's a win-win situation, both for drug companies, for patients, as well as for us societally, as we're having to pay for all of this. So AI, as you saw from my colleagues' talks, can increase efficiency in clinical trials in various different ways, from drug discovery to optimizing trial design to patient recruitment to effectual execution. The two that I'm going to focus on today are primarily optimizing trial design and patient recruitment. So how do you optimize study design? And one of the big pieces around this is being able to select trial populations, and Christina presented on this very elegantly. But using AI can help you reduce population heterogeneity. And what reduction of population heterogeneity does is it means you need smaller clinical trials because the variability is less. It enables you to enrich for patients who are more likely to develop an endpoint, whether that be patients that are faster progressors, or you to predict, whether that be patients who are faster progressors, or it be patients who are more likely to have a measurable clinical endpoint, such as, for example, if we're looking for patients who are more likely to go for intermediate AMD to advanced AMD, or patients who are more likely to develop neovascularization, or patients who are more likely to develop growth of their geographic atrophy, there are certain predictive things that you can look for in images. Some of these have been published on, such as hyperreflective foci, for example, in patients with intermediate AMD or drusen volume that we know of. And there are others, as Christina was saying, that we may not be aware of. And so what AI helps you do is do prognostic enrichment and help identify patients that are more likely to progress, especially with respect to the particular clinical trial endpoints that you're looking at. For example, Stefan was talking about using sensitivity at the margins, inferred sensitivity at the margins of these GA lesions to kind of predict who are more likely to progress over time. It also helps us do predictive enrichment. So you may choose for faster progressors, but as Christina was saying, those faster progressors are not necessarily the ones that are most likely to respond to the treatment that you're administering, right? And so predictive enrichment, kind of to try to predict which cohort of patients are most likely to respond to the therapeutic interventions that you're trying to test, can also be very, very important in optimizing the efficiency of the trial population that you choose for your study design. Now, this is from Ursula's work, and this is more along identifying patients for clinical trials. So AI assists, for example, in the classification of GA to confirm GA presence, to quantify lesion size, to match specific trial criteria such as GA area and location relative to the fovea, and can be really powerful because it can dig through large data sets in clinical trials and can be used to identify patients at particular clinical trial sites. AI can also be very useful in identifying diabetic retinopathy. So we know that AI can identify referable diabetic retinopathy, but very importantly for clinical trials, those same algorithms can be used to identify DRSS grading, as Amita was presenting on, as well as to identify patients who have DME and don't have DME. So here is a study that was conducted out of the Moorfields Clinic that looked at patients who had been identified by manual classification, and then went ahead by just looking at the EHR, and then went ahead and looked at this AI model. And so conventional EHR searches resulted in an eligibility rate of 40%. AI algorithm increased the eligibility rate to 63%. That's over a 50% increase in the efficiency of looking for these patients using traditional patient searching mechanisms, using AI EHR and imaging modalities. So one of the other kind of things that we're doing, so we talked a lot about trial to patient matching. We talked a lot about trial to patient matching, which is matching one trial to a list of candidate patients in at clinical trial sites, for example. But there's also patient to trial matching. So patients who have more rare diseases, for example, or even patients who have more common diseases, AI can be used to match one patient to a list of candidate clinical trials. And this is something that's actually being taken on by the NIH now, and they talk about trial GPT to lower screen fail rates and to decrease the recruitment period for these patients for clinical trials. Trial GPT can reduce screening times for patient to trial matching very significantly when the NIH has looked at this. And of course, this has been published before, as you can see over here. And this is actually a really interesting publication to look at for anyone who's interested in clinical trial design. What about AI for patient monitoring and endpoint measurement and all the cool mechanisms that we have to be able to grade images using AI? But the success of AI in clinical trials fundamentally depends on the quality and quantity of data, though, that it can access, right? So we talk about overfit in certain situations and also making sure that the AI algorithms that we have are diverse enough to be able to handle the diverse populations that they are going to be applied to. So what are the challenges to AI adoption in clinical trials? And the key challenges, of course, include robust real-world performance, generalizability across diverse populations, and then the interpretability of the results that you're getting. AI models can be biased if they're trained on limited or imbalanced data sets, and that's really important to keep in mind because you don't want to go in there and expect a certain level of efficiency and end up with much lower efficiency of those AI models. So the key take-home message is that AI holds immense potential to make clinical trials in ophthalmology more efficient and insightful. We've seen huge exponential benefits over just the last 5 to 6 years. And then, we expect to see more progress as we apply these to real-world clinical trials at this point. I'm going to end over here and thank you so much for your attention.
Thank you so much, Nadia. That's a great talk and a great summary of all the potential that we have for AI in clinical trials. I would like to invite the speakers back on podium. Thank you so much. We have just a few minutes to finalize session number 2 with your big picture talks and thoughts around the potential for AI in patient care and as well as clinical trial and the great work patient care in the sense what we learn in clinical trials drives our preferred practice patterns. So a high level question to the group and I'm open to all of you to address. The science is so advanced and we've been seeing the majority of work towards the end of a clinical trial life cycle with the data analysis and post hoc analysis and better interpretation. Now we're starting to see some implementation before the clinical trial starts with patient pre-screening, patient screening. In your experience, what are the main barriers to implement AI in the live prospective clinical trial? Why uptake has been so slow?
So, I'm happy to talk about it a little bit, and I think other people may have more context to this. I think one piece is that a lot of the AI algorithms that are out there exist in relative silos, and it's and they're not ready for implementation at the clinical trial site level. And it's often hard to get these various different companies and groups to speak to each other and consolidate these things. And I think for me that has been one of the bigger challenges. We're very pro incorporating AI in clinical trials, and it has still been really hard, right? And then I think many of them obviously don't have the appropriate data, don't have the appropriate validation, don't have the publications in place that you would expect to see because people are hoping to generate revenue out of this, but kind of trying to shortcut some of the robust work that it takes to be able to publish on them and be able to generate that data.
Thank you, Nadia. Amita, you've been doing so much work in pre-screening for DR.
Yes. Yeah. That's a great question, and I agree with what Nadia said. And one of the things is with models, there is the regulatory acceptance for clinical trials, and then the trust of the physicians. Even if, you put the regulatory piece aside for a moment because that's so difficult to handle. So, we have classifier models, we have segmentation models, we have prediction models. Christina presented some of the prediction pieces. Segmentation ones are the easiest, low-hanging fruit, I feel, for ophthalmology, because you see what the model is doing. So GA areas, fluid segmentations, easy loss, Rosenwald, you see what it's doing. So despite lack of robust validation, if you want to use it for a trial, try it out on something, see for yourself how it's performing, and use it. I think that's adaptable. But the classifier models and prediction is a little harder because of lack of explainability, and the trust comes with that. I think that's where the tie-up is.
Yeah, completely agree.
Yeah, I would like to catch up on this, Amita, what you said, as a very experienced reading center person that you are. So it is very clear that we need to come up with biomarkers and biomarker assessment that is tangible and has a clinical context and comes with clinical insight, because the clinical trials are preparing the path towards treatment of true patients in the real world. So the biomarkers have to be accessible, and segmentation is measurement. Measurement is very clear, can be validated in a very transparent and obvious manner. And this is where we should start. And then we can slowly take one step after the other. So if we know how to segment the EZ thickness and the RPE loss and EZ loss, we can introduce a parameter that correlates different segmentation measurements, such as the EZ-RPE loss ratio, which turned out to be a very important predictive factor for disease activity, just like we know fluid in neovascular AMD is a feature of activity. So I think that this is where we need to start.
Thank you, Ursula.
Yeah, do
Yeah.
I have a couple of seconds just to chime in? I totally agree with everyone what was said, and I would actually just put it very simply into maybe three things: that we need a consensus. We don't have a consensus as a group. We are apparently not that we're going to want to rely on, whether that's for the diabetic retinopathy, 45-degree ultra wild cameras, whether we are going with the OCTs or not. So we need to sit and discuss that first. Then we have to validate everything that we are doing so that actually we can put it out there. Data set bias is a big, huge problem. We don't want to overrepresent staging. We don't want to overrepresent ethnicity. So that's another problem that we have. And then also safety and regulation. I think that's going to be the biggest hurdle if you want to roll out wide. But I think what we need is we need a task force people. They're going to sit, they're going to discuss what's needed out there. We have to make a plan and push forward. And I think that's the biggest problem why we are not wider accepting AI in the clinical trial world.
I can maybe add a little bit of stats perspective here also. I think working in a large organization, what's really important is to ask the question like why, and like quantify the benefit and also the risks. And you saw that maybe in my presentation, like, why should we implement a very kind of complex model, getting that into the GXP compliant workflow? So is it worth the effort, right? And that's why we came up with these metrics: effective sample size increase, for example, for cohort adjustment, telling people how much do you gain by doing that, right? Like really trying to quantify what's the benefit and that we are making better decisions. So that's one thing, but then also quantifying the risk, right? So for cohort adjustment, it's a very low risk use case. You basically cannot harm yourself. So that's very important to explain to people, but a lot of people are still uncomfortable to put that into the primary analysis, right? So that also requires a lot of explaining why that is a very safe use case. And I really liked what Amita said about the pre-screening, same thing, right? Really quantify how much you reduce the screen failure rates, maybe how many more patients you can find, but also making sure you understand the risk. Like you talked a little bit about like watching the false negative rate, making sure your negative predictive value is really high, you don't bias the study population. I think we really need to be very specific on what we gain from using these models and what are the risks.
Thank you. And the sentiment that the panel is expressing here is ethical implementation, careful implementation, safe implementation. And the other side of this world, Maida, your work showed, we have large language models that are broadly available to the public. And we are seeing now unregulated devices do that kind of clinical prediction. So it's such a fine balance. And I do think I'm thank you, very grateful for the work this group collectively is doing here in putting the bar very high in terms of ethical and safe implementation. But then now what, right? There are all those tools available for patients. And Stefan, it's possibly your line of work will also become an interesting educational tool for patients, but likely it will need to be regulated to be made available. Stefan, would you like to close with final thoughts?
Yeah. So I agree with all what was said, and I think there are different levels of quality we need. If it's just an educational tool and not interfering with patient management, I think the barriers are much lower. But if it's used for clinical trials, obviously we need very high quality. Trying to implement AI in our own institution, on the institutional level, the biggest aspects are data protection and actually that AI will jeopardize physicians to make treatment decisions. This is their biggest fears.
Yes, unfortunately, which was extensively discussed in the first session. Well, thank you all so much. It's been an honor and a privilege to have you joining us today. And with that, we're going to close session 2, and I would like to invite the Genentech sponsored talk to the panel. Thank you.
Thank you, Danielle. Thank you, Daniela.
Hello, everyone, and thank you to the organizers. My name is Alexandra Warder. I am a retina specialist and medical director at Genentech Roche. Today, I'll focus on how deep machine learning and AI can help us extract more meaningful information from OCT imaging, with the goal of improving disease assessment, predicting outcomes, and supporting more personalized retina care. These are my disclosures. I'd like to start with our faricimab real-world data program. This work sits within a broad real-world data effort with over 200,000 patients in Roche-sponsored studies and more than 7,000 in independent studies. In both NAMD and DME, we see that vision gains observed in our clinical trials, such as Yosemite and Rhine and Tenaya and Lucerne, are maintained in real-world settings. From an AI perspective, this creates an important opportunity. Can we go beyond broad outcomes like vision and CST and use OCT imaging to better understand disease burden and treatment response? I'd like to start with this case as it illustrates a core idea. Here we see an original B scan, a single two-dimensional OCT scan where we can observe intraretinal fluid, subretinal fluid, hyperreflective foci. But here we're only seeing a part of the disease. With AI-based segmentation, we can analyze the same eye in a 3D image and quantify fluid volumes and lesion volumes across the entire retina. Here we see HRF in red, IRF in green, SRF in blue. This shifts OCT from a largely qualitative tool to a volumetric, more objective measure of disease burden. I'd like to start by introducing some of our post-hoc analyses done in our Yosemite and Rhine trials, beginning with our first example of intraretinal fluid in DME. Using machine learning, we measured IRF volumes across 97 OCT-B scans per patient in 798 patients from the phase 3 Yosemite and Rhine trials. Patients were grouped by IRF reduction after 3 months, similar to the rationale of Protocol I post-hoc analyses. The key findings were that patients with more than 50% IRF reduction had significantly better BCVA at 2 years, and about twice the proportion gained at least 15 letters compared to those with minimal reduction. Here, AI is not just augmenting segmentation here, it is generating a volumetric biomarker that may help predict long-term functional outcomes. Our second example is that of hyperreflective foci, or HRF, another potential biomarker in DME. Using deep learning, HRF were segmented as objects smaller than 50 microns across full OCT volumes. Greater baseline HRF volume was associated with worse DRSS severity, thicker CST, and lower baseline visual acuity. We also saw co-localization between HRF and IRF, suggesting that automated volumetric analysis can reveal spatial biomarker relationships that may reflect underlying disease biology. The third example is that of heart exudates. Here, using deep learning, we used this to quantify heart exudate counts and volumes across OCT volumetric scans up until week 100. At baseline, 81% of patients had more heart exudates, and these patients tended to have features of greater disease burden, and they also showed slower early improvement of CST and BCVA. This, of course, outcomes later became similar. Again, AI turns a visible but difficult to scale lesion, like heart exudates, into a standardized quantitative biomarker that may help with patient stratification and response assessment. So to close, deep learning allows us to quantify OCT biomarkers objectively and at scale, link structure to function, bridge clinical trials with real-world data, uncover novel biomarker insights, and move towards predictive and personalized retinal care. Thank you so much.
Thank you so much, Dr. Warder, for presenting all of those wonderful biomarkers that AI has helped to discover and to explore in the Yosemite and Rhine databases. We will now move on to session 3. I'm Jennifer Lim, one of the co-directors of this OAI meeting, and it's really wonderful to have all of you present with us today. Our session now is on advances in AI for diabetic retinopathy and beyond. Our first speaker of this session is Dr. Alice Lorch, who is the Assistant Professor of Ophthalmology at Massachusetts Eye and Ear Harvard University, Associate Chief Medical Officer, and Vice President of Medical Affairs. She's done a lot of work on community implementation of diabetic screening, and she'll be speaking on real-world implementation of diabetic retinopathy screening with AI. Take it away, Alice.
All right. Good morning, everybody. Thank you. I'm thrilled to open this session. And I'm going to build on the discussion that we just had in the last panel, because what I'm going to talk about is something that I truly think will determine whether AI transforms ophthalmology, which is implementation. Much of the conversation that we have around AI focuses on algorithm development and performance, and those advances are obviously exciting. But I'd argue that ultimately the impact of AI will depend just as much on how successfully we integrate these tools into the real world clinical practice of our everyday work. And to illustrate that point, I'm going to be sharing our experience at Mass Eye and Ear and how we built and scaled diabetic retinopathy screening programs in our community health centers, and then how we transitioned from a traditional teleretinal screening program to an AI-based screening program. So when we think about AI innovation, we often are talking about things like model development, training, trials, but implementation science asks a slightly different question. And we ask, how do we actually take these technologies and how do we get them to patients so that we can improve patient outcomes at scale? For diabetic retinopathy, we already know the clinical problem. We know that screening works. We know that AI has really tremendous potential to address gaps in screening. But we also know that even the very best algorithm we have is not going to have impact if the patients are not actually screened. If we don't get the technology to the patients, if we don't capture their images, if we don't put their images in the EMR, and then if we don't actually refer patients who screen positive in and follow up on them. or if our workflows are not sustainable. And so in many ways, when we think about the implementation of diabetic retinopathy screening with AI, the implementation can be the rate limiting step that limits the promise of AI if we don't get it right. So our journey at Mass Eye Near began several years before we were even thinking about AI. And from the onset, we were thinking about a screening program with cameras. And what we realized from the very beginning is that the screening program requires a lot more than just acquiring a camera. We needed all of these things. We needed financial support. We needed to get the machines. We needed to work with partners in primary care. We needed to work with IT, design workflows, put together referral patterns and pathways, and also think about training of how we were going to engage our physician staff who were going to be involved in this program. And every single one of these steps really required stakeholder engagement and required ongoing relationship building. And so we realized that the technology itself was really one component of the system that we were putting together. Our initial model of screening was a very traditional teleretinal screening program where our fundus photographs were obtained in primary care clinics. They were reviewed by ophthalmologists and followed up according to what was found in those images. And by 2025, we had been doing this in 5 community-based sites for about 4 years. You can see these sites here, and in 2025 alone, we screened a little over 1,000 patients. This was sort of as our program matured. We found about 21% of them actually needed referral for future evaluation. And you can see here how those screenings were split up. So the teal segments here represented the in-person examinations that patients were getting and continued to get even when our program was in existence. The light blue segments show the patients that we were screening with our program, and the dark blue patients show patients that were still not being screened in each one of our primary care clinics. And so looking at that, you can see even though we were improving screening rates by placing these cameras in the clinics, there was still this large dark blue group of patients who required screening, who needed screening, but remained unscreened. We have done a lot of work trying to encourage these clinics to ramp up implementation, and I will say that it requires constant attention and really some hand-holding. We provide weekly lists of all of the patients in each site that are eligible for screening. We provide on-site support. Even given that, only a proportion of eligible patients each week are actually screened. And when we talk to our clinics about why this is happening, they tell us that they are stretched thin. We know that there are many priorities for primary care. They have competing priorities and only can put so much of their resources into this program. Some of the things that are encouraging about the program as we build it up is that we do see sustained improvement over time. So although we haven't been able to reach as many patients as we would like, we do see improvement, and this is one site over the course of 5 years. You can see that we decreased the proportion of diabetic patients who were not receiving screening from 72% initially to 43% ultimately. But again, we still have 43% of patients who are not being screened despite having access to screening in clinics where they're receiving their primary care. You can see here we published this work and we compared our own community health centers where we had these cameras to sites that did not have cameras that were similar sites. And our participating sites showed really a significantly greater improvement than would have been expected compared to the comparable sites. But again, patients in compliance, you can see here, were somewhere between 40 and 50%, so really a lot of room for improvement. So after we established this infrastructure for a teleretinal screening program, we began our transition to AI-assisted screening, and the workflow became simpler. So instead of having images that needed to be reviewed by our ophthalmologist, these results were being transmitted immediately and rapidly at point of care, which was really a benefit for providers and primary care clinics as well as patients. But this didn't change our implementation challenges. So the efforts that we had to make to still get this to patients still really existed. And you can see here how this worked. Images were captured using a TopCon camera. It was analyzed by an AI system. The results were returned to the electronic medical record. The ability, again, to get these results right away created a fundamentally different experience for patients and providers. But again, implementation matters. So we looked at our numbers and looked at how many patients in this cohort were actually getting the screening with AI and still found that we had a lot of room for improvement. And you can see that here. So over the past year or two that we have implemented AI into these clinics, we have screened over about 3,500 patients. 18% of these patients screened positive, and 28% had ungradable images. And our screening is very variable. So this is all the sites that we're in. We're about 20 sites within our system. And you can see some sites are screening very high numbers of patients and some are very low. And this has many factors. There are leadership buy-in issues, bandwidth, patient demographics, and all of those things determine really whether these technologies get to our patients. Right now, we don't have a financial incentive for uptake because we have a grant funded model. So the sites aren't getting any financial reimbursement for doing screening, and we're working on that new model and hope that when there is reimbursement, that will create more incentive, particularly in underfunded primary care settings. This is a cohort that we looked at in our early review of our data, and we found that in this group, among patients who completed follow-up, about a third of them actually were found to have diabetic retinopathy or diabetic macular edema, and then a subset of those ultimately required treatment. I think this was very positive for us because it demonstrated that the program is really identifying clinically meaningful disease. But this data also highlights one of our greatest implementation challenges beyond just getting the cameras to patients, which is once we have screened patients positive and want to get them into our clinics, we still struggle in completing follow-up for patients. And another limitation to how AI will ultimately impact and improve patient care. And finally, another thing that we're constantly thinking about is financial sustainability. This really remains a critical issue. As I mentioned, we are working to build a model in which reimbursement will flow to our clinics who participate, and we hope that that will increase the incentive for participation in screening. There is also a potential population health financial gain that we are working on with contracted payers, and I think that's another thing that will really help move implementation and get this to more patients. However, I think it has to be said that while financial pathways do exist for reimbursement, many programs like this still require some institutional support when we are setting them up, when we're instituting them, implementing them, and scaling them. This isn't something that's immediately sustainable, and so that has to be planned for as we're taking this AI and implementing it in real-world situations. So as I conclude, I want to leave just a few lessons from our experience. The challenges we face today in getting AI to improve outcomes and really change the face of ophthalmology, I think, are not solely algorithmic. We have to think about implementation challenges, and these are some of the ones that we have been working on. How do we sustain programs financially? I spoke about some of that, and I think that is something that is quickly evolving. How do we automate referrals such that when we screen patients positive using this technology, we actually make sure that we get them in and provide them the care that they need as a result of this technology than the things that we found? How do we improve follow-up completion? There are many patient-centric factors we have to think about in doing that and making sure that we achieve the value of having this screening. And how do we achieve consistent adoption around sites, knowing that there's a lot of variability, as I showed you. These are all the questions that we have been working on as we implement and the things that we're thinking of. And I think that these are the questions that are really going to determine whether AI achieves its promise and whether we can build solutions for implementation that gets all of these technologies to patients. Ultimately, the future impact of AI in ophthalmology, I think, depends on making sure that we can integrate these tools into clinical workflows, and focus on implementation science will be important to get all these amazing technologies we've heard about today to actually improve the care of patients that we serve. So thank you very much.
Thank you so much, Dr. Lorsch, for sharing your expertise. That was a wonderful presentation. You really touched upon all of the issues required for implementation of AI for DR screening, and it was very granular and very well done. So thank you so much, and I look forward to the discussion. Our next speaker is Dr. Homa Rashid-Disabit, who is an assistant professor of ophthalmology at UIC and one of my great collaborators and new colleagues at UIC. And she'll be speaking on classifying diabetic retinopathy through retinal signatures and fundus images. And Homa is really working to get AI into the user's hands to make it clinically useful. taking deep learning algorithms and applying them to clinical use. So take it away, Dr. Rasha Disabit.
Thank you so much, Jenny, for the kind introduction and the invitation. I'm so excited to talk about our recent work on the diabetic retinopathy and fundus analysis. So with that, let's start with the main application of this study, which is DR. Diabetic retinopathy is a leading cause of vision loss and currently is affecting over 100 million people worldwide. And with the recent advancements of AI and all the great talks we had today, this morning on the AI for diabetic retinopathy, there has been a great promise of AI to work for classifying different stages of diabetic retinopathy. And many of the seminal works in the literature have tried to distinguish between different stages of DR, including mild versus moderate versus severe versus proliferative DR, as well as regrouping these cohorts differently to make it more meaningful clinically. However, one of the missing keys in this diagram or pipeline for DR prediction is diabetic mellitus, which diabetic mellitus, abbreviated as DM, without retinopathy is a prerequisite for DR. Yet it's overlooked in the previous studies to incorporate that explicitly within the DR prediction pipeline. And usually in many cases in real world, there is a prolonged period between DM no DR and development of DR. So being able to model that stage explicitly within that pipeline, we could potentially improve the early detection of DR. So with that, our contribution in this study specifically is to explicitly modeling and incorporating DM without DR patients within the DR severity spectrum prediction for potentially improving the early detection of DR, and also quantifying the key features of fundus images, including optic nerve head and retinal blood vessels, importance on DR prediction and the AI performance by perturbation analysis. And finally, we have characterized the spatial changes in AI features across different DR stages. We have used a subset of UIC fundus data sets. UIC data set is real world clinical data, so it has high variability and of course, so much noise. So we have first pre-processed the data to filter out those images that do not have optic nerve head visible. And we have used in total about 6,069 fundus images. And here I have in the table the breakdown of the number of images used across different cohorts that we have studied in train validation and test set, and a couple of examples for each class to show the images. So our methodology in this study has three main phases. In the first phase, we have created three different classification models to study whether the AI can distinguish DM without DR versus no DM cohort, as well as the mild DR, which is the earliest stage of DR. Our first classification model only uses the three cohorts classification. The second model we created includes four classes of no DM, DM without DR, mild DR versus referable DR, and the six-class classification model we have created includes no DM versus DM without DR, mild DR, moderate, severe, and PDR. And for all of these models, we have used extensive hyperparameter search to tune the model, optimize the models. And we have use ResNet 50, ResNet 101, as well as DenseNet 121 as the hyperparameter for optimizing the models. The second phase of our study, our methodology includes segmentation modeling of vasculature, the retinal vessels, as well as optic nerve head. For each one of those, we have created a segmentation model, and then later on, we have used Gaussian noise to perturb those anatomy, because later we wanted to see what's the impact of each one of those anatomies on the DR prediction. And then the final piece of our methodology, the third phase, is just the pipeline for quantifying the spatial retinal features location, where we use the saliency of the AI and we anchored it against the optic nerve head to be able to see location-wise how would that features or retinal signature across these different cohorts change location. Here, I'm summarizing our DR classification results for each one of the classification models. We have created 3-class, 4-class versus 6-class. And our 3-class model achieves an average AUC of 82%. And if you look at the orange curve, it's summarizing the AUC for the DM without DR. That is achieving, the AI is achieving 80% AUC in the 3-class manner, as well as like 72% performance for distinguishing DM without DR versus other cohorts of the study when we used it in a 4-class classification manner, and the AI was able to distinguish DM without DR with 66% performance when we incorporated all the 6 stages of DR and cohorts, which actually is showing that there is some retinal signature that AI can pinpoint and pick up to be able to tell apart from other cohorts, and DM without DR can be distinguished in the fundus images. So, here I'm summarizing the results for the 3-class classification model when we perturb the optic nerve head versus the vessels. And on the red font, I'm showing how much was the performance degradation after corrupting that anatomy. And we can clearly see that when the vessels were perturbed, there was a significant major performance drop in the DR prediction. And what that shows is basically model is heavily relying on the vasculature vessels to predict DR as well as other cohorts. And the optic nerve head had mildly influence on that prediction. The result was pretty consistent when we use it for the 4-class classification and 6-class classification. So I'm not going to bother you to read all these tables. And also, we looked into the shift in the retinal signature location across these cohorts. On the left-hand side, I'm showing just one random image of each cohort as side by side by the AI saliency, or where the AI was paying more attention to predict the downstream task of class predictions, as well as the optic nerve head mask and the binarized AI saliency that we quantified this location-wise change. And what we found out is that there is a significant positive correlation between DR progression stages and distance from optic nerve head. So it seems as the DR progresses, the features that AI is looking at shift away from the optic nerve head. So in conclusion, we found that there is a retinal signature in fundus images that can be detected by AI and can distinguish DM without DR from the mild DR. So hopefully we can use this to further improve the early detection of DR. And the model was accurate by the performance of 82%, 77%, and 70% using finer granularity in the cohorts of 3-class versus 4-class versus 6-class, and approach has shown that the vessels are dominant predictive cue for this distinguishment across these classes, whereas optic nerve head doesn't have many signals for this classification. However, one important note is that while vessels are showing 30% of the information on them, however, 2/3 or 70% still is extra vasculature. So as the next step of this study, we hope to look into the OCT data to be able to see outer retina layers information. And with that, I would love to conclude my presentation, and thank you so much for your attention.
Thank you so much, Dr. Rishit Disabet. That is wonderful work that you've shared with us today, and very important because there'll be new drugs, obviously, that are looking at preventing the onset of diabetic retinopathy, and obviously we'll need algorithms to go ahead and address that. I'd like now to turn to our next speaker and introduce my great friend and colleague, Dr. Catherine Talcott, who's a vitreoretinal surgeon at the Cole Eye Institute and associate professor of ophthalmology there. She's done a lot of work in clinical trials and is also a great surgeon. And today she'll be discussing quantitative ultra-wide field angiography in diabetic retinopathy. Kat, take it away.
Awesome. Thank you so much for the kind introduction. Here are my disclosures. And as we know, in retina and diabetic macular edema overall, we can see one patient's OCT, such as someone who has a lot of edema present here. But even though their OCT may look the same, they can actually come from very different types of patients. It could be a patient who doesn't have a lot of leakage or ischemia on their FA. But if you look at the FAs for some of these patients, they can have a lot of ischemia and leakage. And so even though that edema looks the same, they're quite different diseases overall. And this really represents sort of unmet needs in the field of diabetic eye disease. There's a lot of variability in the natural history, how patients respond to therapeutics, and what their prognosis is. And ultra-wide field angiography really has a lot of information that's untapped. Currently in the clinic, if I'm looking at an FA, I'm just looking at some of these features, but it's hard for me to put a patient's features in context of overall populations. And so, unfortunately, there's really limited understanding of the role of quantitative data from ultra-wide field angiography in diabetic eye disease. So we've heard some about it in the earlier presentations today. So in this movement towards sort of quantifying some of the features that we see on ultra-wide field angiography, our group has done a lot of work on this. And the initial platform was looking at traditional imaging processing algorithms to be able to quantify these features, enable disease burden, as well as to see how we can track these things longitudinally. Some of the things that we've looked at is counting individual microaneurysms. Other things that we can do is we can also look at leakage, and that's present here on the right on the FA for this patient who has a lot of leakage. And you can also identify areas of ischemia shown here in blue. After these metrics are looked at for some of these patients, you can actually use different tools to be able to quantify and give yourself an index as to what the measures of these different features are. So we looked at the ischemic index, which is the percentage of ischemic retina calculated based on the total visibility or analyzable retina that's present. Similarly, you can do that to look at leakage, and that's reflected in the leakage index, as well as counting individual microaneurysms to be able to see what the burden is in a certain region of interest. The next generation, though, is really taking, rather than looking at the FA and individually marking every microaneurysm, which is very tedious, as you can imagine, and using AI to be able to look at this. So we can use vascular network extraction and analysis. This is a normal eye. We can also apply this to patients who have diabetic retinopathy, including this patient who has proliferative diabetic retinopathy. And so the next step is sort of how we can sort of quantify some of these changes. We've done this looking at microaneurysm counts and seeing that it really does vary depending on the severity of the disease in terms of the microaneurysms that are present. We can get a sense of how much leakage someone has by looking at their by looking at their leakage index, as here. And we can do the same thing for ischemia to be able to understand their ischemic burden as well. So what we wanted to do is we wanted to apply these metrics towards patients who are actually receiving therapy to be able to see if there's a difference that's present. So what we did is we performed a post hoc analysis looking at the HELIOS study, which looked at OTX TKI in diabetic retinopathy. So this was a phase 1 study looking at patients with DRSS levels of 47 and 53. And these patients were randomized to get either OTX TKI or sham. Although the primary outcome was safety, the secondary outcome was change in their diabetic severity, as well as rescue therapy, vision, and CST changes. So what we did is we looked at leakage index in these patients, and this was validated by readers after it went through the AI algorithm. This is the overall result, showing that in the sham patients, they actually had an increase in their total leakage area over the course of the study, whereas patients who received the OTX TKI therapy actually had a decrease in their total vascular leakage that remained stable. And this was the same, including for that leakage index, which corrects for the amount of area analyzed. We saw similar patterns if we looked at peripheral leakage. So those sham patients had an increase in peripheral leakage area and index, whereas the treated patients had a decrease. And the same pattern was seen if we looked at macular leakage as well. Here are some examples. This is the sham patient who had baseline, had some leakage shown in blue and teal on the bottom left, but at the end of the study actually had a significant increase in their leakage. And if we compare this to a patient who received treatment, they had a lot of leakage at baseline in this case, but at the end of the study had less leakage. So I utilize this sort of post-hoc analysis as just an example of the types of information that we can get from applying AI to ultra-wide field and angiography. As we know from a lot of the great talks today, AI really transforms retinal imaging and can allow us to have improved clinical diagnosis as well as quantitative biomarkers. And this is really can help us to be able to decide how to treat patients with diabetic retinopathy. It'll also move treatment towards personalized treatment strategies, where you might be able to gather more information about a patient and just seeing them one time and be able to discern if one treatment might work better for them than others. It's been a pleasure to give this talk to you this morning, and I'm looking forward to our panel discussion later.
Thank you so much, Dr. Talcott, for that wonderful talk and for really bringing it in terms of using AI quantitatively for fluorescein angiography. Our next speaker is Dr. Lucia Sobrin, who is the Charles Edward Whitten Professor of Ophthalmology at the Harvard Medical School at Mass Eye and Ear, and also co-director of the Fellowship in Uveitis. Unfortunately, Dr. Sobrin cannot be here today. She's a great friend and colleague, and I will now let her take it away virtually. Lucia, please take it away.
Good morning. Thank you to the organizers for the opportunity to speak to you about artificial intelligence in uveitis care. I'm sorry I cannot be live with you all. My only disclosures are that I'm a consultant for Roche, and that is not relevant to this presentation. So where are we in artificial intelligence for uveitis care? This is the results of a PubMed search for those two terms. And as you can see, starting around 2020, there's been an uptick in the number of publications in uveitis and artificial intelligence, but that highest bar in 2025 is only 47 publications. And overall, there are only 153 publications or so to date. So really, we're at the infancy of uveitis and artificial intelligence. So I'm going to speak about where AI fits into the uveitis workflow, what's been done so far, and what remains to be done and where we're headed. So there are many places where AI fits into the uveitis workflow. First, diagnosis and classification is one area that's already started to be explored. And because uveitis is such a heterogeneous disease, and because it's so important to distinguish infectious causes from non-infectious causes, and among the non-infectious causes, to figure out if there's an underlying systemic illness that we need to make the patient aware of, really here's an important place where AI can help us, and especially help places where there's not access to a uveitis specialist to do this. There's also been some work already in imaging and monitoring. Uveitis is a disease where we often image heavily, and we rely on imaging to monitor and make treatment decisions. And so AI has the opportunity to help us do this better and faster. It also has the opportunity to help us document clinically better and then take all of these advances in the clinic and inform research by automating phenotyping and enabling cohort discovery. And so we'll explore each of these. We'll start with classification. The biggest effort in uveitis classification and artificial intelligence has been by the standardization of uveitis nomenclature working group. They published a special issue of the American Journal of Ophthalmology looking into applying machine learning to classifying the different kinds of uveitis. To do this, they assembled almost 6,000 uveitis cases. They had uveitis specialists look over them, decide on a diagnosis, and then they used machine learning methods to develop classification criteria for 25 types of uveitis. And across the many types of uveitis, you can see an example of one of the publications here on serpiginous choroiditis. The validation was quite high with an independent data set, greater than 93% across all of them. So this really established the first framework for reproducible classification of uveitis entities. This is just a starting point. The clinical impacts are that it will help us to standardize enrollment for clinical trials. So we're all talking about the same disease when we're planning to enroll that disease in a clinical trial, and also as a foundation for other future diagnostic support systems. AI has also been explored for imaging in uveitis. This has been primarily in grading anterior chamber cell on anterior segment OCT, grading vitreous cell in different ways, and also segmenting and quantitating retinal vascular leakage in uveitis patients. Here are some example images of what's been done so far. So you can see on the left side, there is an anterior chamber OCT. In the top panel, there's very few cells. In the bottom panel, there's a lot more anterior chamber cell, and the machine learning AI method has segmented the anterior chamber and segmented each of those cells in the anterior chamber. On the right side, you can see wide field fluorescein angiograms and how the leakage has been quantified and identified by the AI methods. And this is very important because many treatment decisions that we make in posterior uveitis are based on improvements in leakage, and anything we can do to better quantitate that and do that in a faster way so we don't have to look through all FA images and compare them ourselves will really help clinical care. Generative AI and large language models also have a role to play in uveitis. Really the helpful thing here is to generate differential diagnoses, help us make decisions clinically about patients, and also to generate patient education materials. So for one study that's looked at chat boxes and compared them to uveitis specialists has found that the diagnostic performance remains below that of experienced uveitis doctors. And in particular, the chatbots struggled with rare diseases or nuanced pattern recognition and their diagnostic ranking, which means they were able to include the true diagnosis in the list of in the differential diagnosis, but it was lower down than it was for the uveitis experts. So this first pass at looking at automation of diagnosis demonstrated that its potential is there as a supportive tool, but at this point, definitely not an autonomous decision maker. There are challenges we face that are specific to uveitis in implementing AI in care, and there are also the general challenges that we face across the board. Specific to uveitis, a lot of our patients' images have issues with quality, either because of small pupils, because of synechiae or vitritis or vitreous haze, and so that limits our ability to use the images. It's a relatively rare disease, so it's hard to get the large numbers we need to train models, and it's also heterogeneous, and we have to image multiple parts of the eye to really get a global view of what's going on. And then there are the general challenges that we face across the board, both ethical and health system clinical adoption issues that we always will have to deal with, no matter where we apply AI in medicine. So what might the future look like? I think in the near term, we'll see more development of automated inflammation scoring. we will see AI-assisted image interpretation and clinical documentation assistance or diagnostic assistance. Longer term, it would be great to get etiology prediction models, giving the probability of a certain type of diagnosis and also predicting the course of disease to help us decide about how aggressive to be about treatment. And I also see digital biomarkers for clinical trials being very important in the future, and the AI can identify those for us. So the take-home messages are that the most mature applications at this point in uveitis care for AI are disease classification and imaging analysis, and they're still in their infancy. Generative AI can support clinical workflows, but currently not quite as good as uveitis specialists for diagnosis. Major challenges remain related to data set sizes, validation, and the things we've talked about in terms of bias and implementation. And the most likely future is clinician-centered AI augmentation rather than autonomous diagnosis. Thank you so much for this opportunity to present.
Thank you so much, Dr. Sobrin, for that wonderfully comprehensive talk. We are very fortunate to have Dr. Sobrin. She's one of the leaders in uveitis. And as I said, unfortunately, she can't be here live today. I'd like now to introduce our next speaker, Dr. Suvik Mukherjee. Dr. Mukherjee is a research fellow at Harvard in AI and ophthalmology. And before that, he was at the NEI, where he worked in hyperspectral imaging and biological images and large-scale data sets. So today, Dr. Mukherjee will be speaking on AI-driven hyperspectral oximetry reveals oxygen hyperextraction and hypoperfusion and macular atrophy. Take it away, Dr. Mukherjee.
Hi, thank you. Hello, everyone. Thank you for being here. I am presenting our preliminary work on quantifying retinal hypoxia in atrophic macular disease using hyperspectral oximetry. Next slide, please. Hyperspectral imaging is traditionally utilized in remote sensing and by NASA for satellite imaging. Instead of capturing a standard RGB picture, it requires a single image across multiple wavelengths. For our dataset, we capture a hyperspectral cube ranging from 450 to 900 nanometers with a very tight 5 nanometer spacing between each wavelength. Next slide, please. To understand why this is useful, consider real versus artificial grass. In visual RGB spectrum, they appear identical to the human eye. However, in the infrared region captured by hyperspectral imaging, real grass shows a massive reflectance spike due to its water content, while artificial grass remains flat. These distinct spectral signatures allow backend classifiers to easily distinguish between visually similar classes. Next slide. Our group previously applied the concept to age-related macular degeneration. They published work demonstrating that different types of drusen, such as hard, soft, and reticular pseudodrusen, have highly distinct spectral signatures. Next slide. This established that we could use a backend classifier to identify these features strictly based on the spectral signatures. Next slide. This brings us to our current study looking at atrophic images from geographic atrophy and Stargardt disease. Our hypothesis is that as vessels atrophy and constrict, blood flow decreases. Consequently, the blood spends more time in contact with the underlying retinal tissue, leading to a much higher oxygen extraction ratio by the time the blood flows out of the retina. Next slide. To test this, we precisely overlapped our hyperspectral image cubes with the corresponding color fundus images. Using previously validated algorithm, we segmented the retinal vessels across our color fundus images. This spatial mapping allowed us to look at the exact spectral signatures occurring within the retinal vasculature. Next slide. Next, we calculated an optical density ratio using specific hyperspectral bands or wavelengths. The numerator is a 600 nanometer oxygen sensitive band, and the denominator is a 570 nanometer isobestic band, which acts as a normalizing reference where the reflectance does not change based on oxygenation. Using a healthy control cohort, we established baselines to separate this ratio into two groups: a high oxygen pool representing the 95th percentile and a low oxygen pool representing the bottom 60th percentile. Next slide. Biologically, the high O2 pool represents the arterial blood flowing into the retinal tissue from the cardiovascular system. Conversely, the low O2 pool represents the venous blood flow out of the retina. By looking at the difference between these two pools, we can calculate the high minus low extraction, which essentially mirrors the artery minus vein oxygen extraction rate. Next slide. Looking at our results from the incoming blood supply, which is the high O2 pool, we found that the values for our healthy controls, the two groups, geographic atrophy and Stargardt patients, look, the healthy controls versus the atrophic group look very similar. The differences were not statistically significant, and the Cohen's d value, which measures the separation between the means in standard deviations, was very low. This tells us that the incoming blood supply to the retinal vessels remains relatively stable across the two groups of control versus the disease. Next slide. However, when we look at the outgoing blood flow in the low O2 pool, we see a drastically different story. In the GA and the Stargardt's group, there is a severe and statistically significant drop in the outgoing oxygen levels. This difference was quite high, approximately 13%, which is with a very large Cohen's d separation. This indicates a significant higher oxygen extraction in the GA group, which aligns perfectly with a previously published paper from literature that I cite later, that found an artery minus vein separation to be about 9% for macular dystrophies. Next slide. This shows the image, the plot, the violin plots of the high minus low extraction between the controls and the Stargardt. And we can see that the mean and also the quantiles have, for the GA or the Stargardt affected group, they have moved upwards. So there is a higher difference or higher oxygen extraction in the affected or the disease group compared to the control group. And the p-value and the Cohen's d-value also says that it's significant, as well as the Cohen's d-value suggests it's higher. Next slide. This is a paper I was mentioning about. They show a artery minus vein extraction jump, or a difference of about 9% for eyes affected with macular dystrophies compared to the controls, which kind of aligns with our result that we are seeing here. In conclusion, our primary hyperspectral oximetry data reveals that while the incoming oxygen supply to the retina remains stable in these atrophic eyes, there is a severe depletion in the outgoing supply. This points towards significant hyperextraction and hypoperfusion in atrophic macular disease. Thank you.
Thank you so much, Dr. Mukherjee, for that wonderful talk and really this innovative work. I'm looking forward to the discussion. I'd like now to introduce our final speaker for this session, Dr. Jochen Kamm, who will be speaking on delivering artificial intelligence in clinical practice with examples from retinal melanoma, pediatric retina, and oculomics. Dr. Kamm is CEO and founder of Prevent Inc. in 2018, and he runs that, as well as multiple prior AI companies which he has founded. And he is really working to leverage generative AI to create adaptive health systems and to look at longitudinal data to give us individual guidelines. So really taking it home to the individual level. Dr. Kamm, please take it away.
Thank you. Thank you for the invitation. Pleased to be here. Yes, I have my disclosures are basically that much of this work was done in the context of some startups, but what I'm showing is pretty straightforward. Okay, I will go very fast about the fact I'm going to mention some AI techniques and approaches, but my focus here is deploying this. And so in the interest of getting to the actual deployment and not worrying about the innovation, I will go fast in the beginning. Next slide. Yes, okay. So I'm having trouble controlling the slides. All right. We have multiple things that we have been able to do over time, from convolutional neural networks to segmentation and generative AI and multimodal AI. All of this is evolving very nicely and actually playing together very nicely. And it is impressive what people have done. We've seen some amazing examples here. And it leads to continuous improvements in performance and efficiency across the board. And then, of course, I think we've heard about this earlier today, foundation models are everywhere, which sets the stage, or sort of encapsulates the idea of having multimodal foundation model approaches. If you look at the top row here, you see that, well, actually look at the bottom row, how incorporating more information and processing the information in a multimodal way can lead you to just have a cleaner, better way forward. And so what I want to mention here briefly is something that we are pioneering right now, which is to actually remove the image from our analysis. And we call this multi-dimensional AI or layered AI analysis. And the concept here is that we are taking retinal images and we are extracting these five dimensions: chronic inflammation, neurocognitive function indicators, metabolic burden, macrovascular and microvascular metrics. And these metrics are basically extracted by the AI using a process analogous to principal component analysis. And they enable us to, in the pioneering work we're doing right now, or the experimental work, is to work with normal patients who want to sort of map the health trajectory. It gives you the ability to sort of present simple trajectories and goals to people. It also allows you to understand the patient in the context of a patient profile. So we're not having to look at the images, we're getting these patient profiles, which give us these metrics that are associated with the names. The other thing you can see here is that we have indicators of whether there has been improvement, because everything we do these days is longitudinal, meaning comparing progress. And within the app, we now have found that, as many others have, that presenting information to the doctor or even to the patient with simple tools that are well known can be very helpful. Here we have a comparison between two time points, which is visually accessible. I should have said that this work is hooked up to a treatment plan at the back end that's also generated by the AI in order to help people select particular lifestyle and nutrition changes. This is clearly an example of oculomics, not a retinal disease. I'm interested in oculomics a lot and work in that, but I will not dwell on it in this moment. I want to quickly dive into a more hands-on example out of an arena called psychiatric retina. Many of you may know about this. We can extract. There's been a fair amount of work done extracting meaningful markers for psychiatric diseases. In particular, we had a pilot study in Brazil where we looked at non-responding patients in major depression disease. Here are some examples that may make sense to you that show typical indicators in the patient population: retina vasculitis, choroidal degradation, and low cup-to-disc ratio, among many others. And so let me remind you, this was a pilot study with only 16 patients. And however, what we find that if you take these multiple metrics and run them through a traditional principal component analysis, you see these distinct different groups. They happen to correlate with patients. And the take-home message here might be that the green group is the group that was subsequently shown to respond positively to ketamine therapy, even though they weren't responding to traditional treatments. And that leads to a larger study that includes biomarkers and more detailed lifestyle assessments. But there's an approach of not having to have experts working with the data in order to develop an application, in this case in major depression disease. And same thing was done in a much more ambitious study looking at Alzheimer's patients. We set ourselves a hard goal of seeing whether known advanced Alzheimer's patients could be understood better. And long story short, in the context of this talk, we did. There's a subgroup of patients that seem to have a much more vascular disease presentation than the typical protein-based. So in the quickly, I mean, if we build these AI solutions, we built them with a bunch of criteria in mind. Most of them are obvious, sensitive, they must be actionable, reproducible. Obviously, we need FDA approval. We need them to be robust, meaning work in multiple populations and setting, and they need to be cost effective because AI is seen often as a cost-saving measure. Regulatory advances have been quick and successful. I don't need to go into the details. Security is always, I mean, now I'm getting into actually deploying this. Security is very, very important. Nice thing is we have the guidelines, we have the techniques, and we now have actually services that make this quicker and enable us to deploy quickly in multiple settings. Autonomous AI, I'm going to skip. We had some comments on this already. I think the time is coming. My rules of thumb for building things is that it needs to be big and small. What do I mean? We need to have lots of data when we build it, but it needs to be well coded small, as in DeepSeek versus OpenAI. It needs to be smart. We don't deploy AI anymore without having some sort of RAG or other analogous methodology employed, meaning it's limited to giving you informed answers. It needs to be actionable. This is the kind of thing that you would plan as you plan out a deployment. As you can see, AI is a relatively small part of this. The grayed out things are things that we decide to de-identify. We use largely the Google Cloud right now. This leads to these very nice Google Cloud platform architectures that hospitals like and require. In real life, I'm having real trouble. Missed the big part. In real life, this looks a bit more complicated, but it is eminently doable. There are many advantages to doing this in the cloud, but the big ones are that hospitals don't need to install new servers and software. Let me go to ROP. We built some ROP interfaces dashboards are very important. Here we see one for the nurses that tells them what exams are coming and when they're overdue, which by the way are scheduled in a collaboration between the artificial intelligence and the actual grader. We can see here, for instance, in the top right that AI can provide, analyze, and examine hospital or site-specific trends, which you would have a hard time doing just looking at images. For those who need it, the AI can pre-populate diagnostic and billing codes, which is often a make or break thing for the user. We generate reports based on the background information. And just to say, we're going away from this idea of having just an AI that's wonderful and sensitive and specific to something that lets you actually manage this in the clinic. Here's a large cohort. The green ones are done. The yellow ones need attention. We have built a very sophisticated interface, that can be used for research or commercially with the AI assisting with optic disc detection and zone detection. It was designed for AI, meaning that the seemingly complex questionnaire on the right is actually fully integrated with allowing us to rapidly update the AI. The whole thing is pre-populated if you wanted to. Last example, because it's dear to my heart, we still work with images. Here's segmentation from Dr. Pagliara in Italy, carefully annotated by hand, choroidal nevi. This is completely without human input, using SAM and YOLO together to do the same job. It does it pretty well, not perfectly. We're in the process of improving that. It is useful because you can identify nevi that grow. It's almost obvious. The other thing in which AI is very useful is that when you have a large cohort, you don't have to look very hard because an artificial intelligence will highlight you both images and individuals. The take-home message is despite all this complexity which we have automated, the basic process remains the same throughout. We have patients, we have processing, we have analysis, and we need to provide results. And this was obviously done in collaboration with many people in Brazil on the depression, in Italy on the choroidal nevi, some of the things around the health metrics are done in California with UCSF, and the RP work pioneered with Dr. Moshfeghi at Stanford. Thank you so much.
Thank you so much, Dr. Combs, for that wonderful overview of how this is all done. I'd like now to call all of our speakers into a very lightning round panel discussion. We have a very limited time because there's just been so much information that we've shared with each other. So please keep your answers very short. Okay, first of all, Dr. Lorch, you gave a wonderful talk on implementation. What is your number one tip for somebody who wants to do this at their own site? What would you tell them to be successfully implementing this and get it to run?
I think it's thinking about this as a multidisciplinary team that extends beyond ophthalmology. I think our successes have been having primary care partners, having IT partners, having partners in our financial offices who are helping us think of this as a really large infrastructure that we're just a small part of.
Wonderful. Maybe you can share your email with everyone. They'll probably want to email you for your tips.
Happy to.
So wonderful. Yes. Thank you. My next question now is for Dr. Rashid Disabit. So Homa, you said about 2/3 of the time the AI was looking not at the vessels, not at the optic nerve. Can you postulate what it might be looking at? And then secondly, in a nutshell, do you think it's because the images were like 45 degrees, and if you used a wider field, you might get better results in the AUC?
Yeah, of course. Actually, I think that would be a great idea to explore. I think the signal that we haven't looked into is around the macula. Right now, the two key features of the fundus we looked into was optic nerve head as well as the vessels. However, we didn't really explore around macula. So we hope that by the next, our future analysis, we look into that spot more, and we hope to see more signature being around that area. And there are some backups in the literature that in more statistical analysis, not AI manner, they have shown there are some signatures there. So that's what we are going to explore next.
Wonderful. We look forward to more work on that and more collaboration. My next question is for Dr. Talcott. Kat, that was very interesting with the non-perfusion index that you showed using the ultra-wide field fluorescein angiography quantitatively. Obviously protocol AA results showed that it wasn't so much the retinal hemorrhages and the findings, but rather the non-perfusion index that was predictive of a two-step progression in 4 years. How does your data compare with the DRCR findings in protocol AA?
Yeah, I think that's a really interesting question. We decided to look more at like leakage than necessarily non-perfusion to be able to see how people respond to that. I don't think we've done the analysis looking at non-perfusion for those patients, but I think it's a good point. It's, obviously our study only looked at about like 20 patients or so. So it just could be that we're not looking at sort of enough of them. But I think for sure it would be helpful to be able to better understand how leakage index versus an ischemic index would correlate for these patients.
Yeah, I look forward to more information on that because, as you know, in the clinic, we always just kind of look at it, but we don't have a quantitative number to peg what we're going to do. I wonder if Dr. Mukherjee is online and just not camera on.
Yeah, I'm on.
Oh, yeah, there you are. Okay, so Dr. Mukherjee, quick question for you. You talked about the low O2 oxygen pool and the differentiation. Have you looked at this prospectively to see whether the O2 pool, if it's really, really low, is predictive of patients who would progress on to say neovascular AMD, or if you looked at vascular occlusion patients, that they would be more prone to get neovascularization because of the ischemia?
No, we haven't. That's a great question. And we would want to look into it. And also longitudinally, if it's able to predict the pool, if it's going to predict whether they are going to convert to late stage AMD, but we haven't done it so far.
Well, we look forward to more work on your end too. And then lastly, but not least, for Dr. Kum, you gave us this great tool for, say, ROP as one example. And you said that sometimes you can link it directly to the billing. Has your system looked at it to the granular point where it looks for specific findings in the exam that are there to support like a level 3 or level 4? Because as clinicians, we're always battling, is this level 3, level 4? Do we have the documentation?
Yeah, so that's an ongoing effort. Now that we have built it and we have expanded it to this level, now we're able to do these kind of analyses very quickly. Obviously, that's not me making the final decision, but it's actually very much a collaborative work at Stanford with a number of doctors. And it now takes us a few days to start looking at the data and incorporate that into the, let's call it a tool for the sake of a better.
Yeah.
So it's meant to be a general purpose thing to enable you to do things that would otherwise be hard.
Wonderful. Well, we look forward to that. Thank you to all of my wonderful, outstanding speakers with sharing your expertise with everybody today. And thank you all in the audience for listening, but don't tune out yet. We have session 4 coming up on oculomics, and this will be run by my great friend and collaborator, Dr. Ted Lang from Stanford. Ted, take it away.
Thanks, Jenny. This has been a really great meeting so far, and we're moving into our oculomics session here, which are our last section of the day. And our first speaker will be a good friend of mine, Mike McConnell, who's a cardiologist here at Stanford and also the Chief Health Officer for Toku Health. And he'll be speaking on retinal AI for cardio, kidney, and metabolic health. So Mike, please join us.
Great. Hopefully this is working. Thanks, Ted. Thanks for the invite to the session organizers. So as you heard, I'm going to talk about cardio, kidney, metabolic health as part of oculomics. And as mentioned, I'm Chief Health Officer at Toku and a part-time clinical professor at Stanford. And see if I can get the button. They said I should be patient to see if it moves. There it goes. Excellent. And then some other disclosures. So cardiovascular kidney metabolic health, or what is now called CKM, it's actually a new paradigm that the American Heart Association developed a couple of years ago, recognizing that these diseases have overlap in some of their pathophysiology, and that if when you have one condition, it can exacerbate the other. But importantly, they have also a lot of overlap in a number of the newer medications that we have benefits across the cardiovascular, kidney, and metabolic space. So the goal is really to view this more holistically, and it really feeds in well with the area of oculomics. But a key thing for me as a, here we go, hit the next button. There we go. Is as a preventive cardiologist, we have all these great guidelines and treatments, but often we're not reaching people sufficiently. A large percentage of the adults in the US have at least stage 1 CKM. And then it's well known that over 50% of patients with core underlying CKM conditions of hypertension, kidney disease, or diabetes are either unaware or poorly controlled. And one of the examples we'll focus on is that over 50% to as high as 92% around the world, that patients where statin is recommended to prevent heart attacks and strokes are not even on this very inexpensive and safe therapy. Oh, somewhere my first earlier slide jumped. Sorry. Yeah, so just to reiterate, there's a ton of science behind the relationship between the retina and cardiovascular conditions, kidney disease, metabolic conditions. You've been hearing certainly around the power of AI for a number of eye conditions, and we'll hear further in additional talks about neurologic conditions. Sorry, jump through that one. So at Toku, we have three main retinal AI products and that relate to CKM health. One is a biologic age assessment. The second is what we call CLAIR, our cardiovascular risk assessment. I'll go into that in more detail. And then our third is for kidney disease risk in adults with diabetes. And as highlighted there, these are in market in multiple locations, and we have FDA breakthrough device designations to help expedite bringing these to market in the US. And the technology is based around multi-layer deep learning AI models that are trained on a wide range of both retinal biomarkers and systemic health biomarkers, sort of as the graphic indicates below, that we identify multiple features and they layer those all up to predict, in this case, highlighted here, a cardiovascular risk model. I'll briefly touch on BioAge and my kidney AI, and then dive a bit more into CLAIR, our cardiovascular risk. But here we highlight several publications where an accelerated bioage actually correlates with multiple markers of either biologic aging or CKM health. So that includes a shorter telomere length, higher prevalence of hypertension, kidney disease, and diabetes, and also worse, what we call a life's essential 8, the American Heart Association's cardiovascular health score. So this is really a wellness product to try to make people aware of their biologic aging and help motivate healthier behavior and evaluation. And my kidney AI, just mentioning that briefly, we did present several abstracts at ARVO, really looking at retinal AI and aligning that with various kidney disease risk scores that are published in the literature, to show that can help predict either kidney failure or developing incident chronic kidney disease. But for CLAIR, we presented at a late-breaking clinical trials at the American College of Cardiology earlier this year, a prospective multi-center trial. So we had 940 participants, age 40 to 75, which aligns with the Heart Association guidelines, and 10 sites split between eye care and primary care with demographic and geographic diversity. And it's modeled somewhat around how diabetic retinopathy is geared towards referable or actionable disease level. For CLAIR, it outputs whether they're elevated 10-year risk for heart attack and stroke or not. The algorithm was run live during the clinical study, and that threshold for risk is our class 1 indication for lipid-lowering therapy per AHA guidelines. So it's designed to be actionable. And then that was matched against the traditional risk score, with then a sensitivity of 91%, specificity of 86%. We had shared with the FDA pre-specified threshold targets for the lower end of the confidence limit, lower end of the confidence interval. And so in both cases exceeded those thresholds. The AUC was very high. Positive predictive value was strong and negative predictive value was very high. Imageability with both cameras, the NW400 and NW500, exceeded 90%. And then we did show consistent diagnostic performance or accuracy across a number of the subgroups, including the clinic type and camera model. So really how we're looking at this is, this collaboration opportunity between eye care as a large front door to healthcare is really well positioned to help detect and improve CKM health via oculomics and empowering this idea of doing healthcare from the eye. It's going to be critical, though, to go from the retinal imaging and AI analysis to ultimately improve health outcomes. We'll need downstream care pathways to help implement guideline-based preventive care. So really collaborative efforts are needed to bring together the eye care and preventive care ecosystems, including evidence generation of outcome benefit, educating patient providers, and having reimbursement models and show cost benefit analyses as well. And as part of this Alliance for Healthcare from the Eye, a group of us have published recently a framework for implementing healthcare from the eye, oculomics, as a powerful window to systemic health. So with core principles around access, patient care coordination, responsible AI, and having sustainable program design. And then as part of it, we've been having regular meetings of the Alliance for Healthcare from the Eye. The American Heart Association recently joined that alliance, and so we're working closely with them to help make sure that we're delivering guideline-based care as a follow-on to our retinal AI products, and also working with the CCOI on a number of the initiatives they have around oculomics. So very appreciative of the collaborative nature of all the work that everyone's doing here. And that's it. Thank you.
Thank you so much for that wonderful talk, Mike. It's really powerful to see how we can impact, healthcare at a population level with oculomics and screening of eye photos. Our next speaker is also a good friend and colleague of mine, Carol Chung from the Chinese University of Hong Kong, and she'll be speaking about the use of oculomics for neurodegenerative disease. Carol.
Thank you so much, Ted. So I would like to declare that I have financial disclosure. I'm co-founder of Eye Cognitive Sciences Limited and Inno Eye Focus Limited. So brain health is a rapidly expanding interdisciplinary field requiring optimization across the life course, irrespective of the presence or absence of disorder. The late manifestations of impaired brain health include common neurodegenerative and cerebrovascular diseases such as stroke and dementia. Strong evidence supporting that screening and early detection of these conditions can facilitate timely intervention and prevent irreversible impairment. The applications of oculomics, we just heard about an excellent talk from Dr. McConnell, and indeed the application of oculomics spans screening, diagnostic assistance, and the prediction of brain diseases and overall brain health. So, for example, dementia is preventable if tackled earlier. So, in 2024, there's a report from the Lancet Standing Commissions. They have summarized there are 40 modifiable risk factors responsible for 45% of dementia. So, if we can manage all these 14 modifiable risk factors, indeed our brain can be changed. For example, decrease vascular damage, reduce dementia neuropathology, reduce stress and inflammation, and also build cognitive and brain reserve. So this is very important because with this in mind that we can actually prevent dementia at primary clinic by a primary care setting by enhancing brain health via these modifiable risk factors. For example, if the individual they don't have any cognitive symptoms, by modifying this, it can actually prevent and dementia in the coming 15 to 15 years before the onset of dementia. So even the individuals with a mild cognitive impairment, by enhancing brain health, it can also delay dementia in the coming 10 to 15 years. In the Chinese University of Hong Kong, so my team and myself, we have developed algorithms from retinal fundus photographs to for detection of Alzheimer's disease dementia based on fundus photographs and OCT. So in the coming few slides, I will more focusing on how we're going to implement our algorithm in real world. So instead of using this as a detection tool for Alzheimer's dementia, so we now focusing on screening suboptimal brain health. So we develop an end-to-end cloud-based infrastructure for screening individual without dementia in the community. So this can allow us to generate a real-time report that is a binary output that needs attention, which means that they are actually the individual at high risk to have suboptimal brain health, and no risk, which means we believe that they have a normal brain health. So by using this algorithm, we actually propose to integrate into the ecosystem for enhancing brain health and brain disease management. So specifically for those that have positive ICOR brain health, which is suboptimal brain health, we recommend them to undergo a cognitive assessment. So if the cognitive assessment showing that is impaired, we recommend them to seek medical assessment for more specialized examination. For example, blood test, MRI, or PET scan, and if they have symptoms that have amyloid, that have mild cognitive impairment, we will recommend them to start to disease-modifying therapies. If the cognitive assessment is unimpaired, so we will look into the modifiable life risk factor assessment. Particularly, we would recommend that they tailor-made lifestyle intervention led by nurses, therapists, other healthcare professionals, or digital technologies. For those that have negative ICOR brain health, we will encourage them to undergo brain health educations, mainly focus to educate them what is brain health, and recommend them to repeat the cognitive this brain health screening, maybe for example every 12 months for elderly individuals over 60 years. So in Hong Kong, we have implement this in a cognitive normal adults in communities. So this is a preliminary data we would like to share with you. So we have recruited more than 800 subjects. So for those that have ICOR positive, we found that they are older age. They have a lower education level, they have lower brain health score, and they have a lower cognitive function score. So these positive individuals are estimated to have, I think there's some delay at my side, to have 20.8 high risk of cognitive decline compared to negative individuals based on worse control in modifiable risk factors. And then we followed a group of patients that they have in after 1 year. So first, we compared those that have tailor-made lifestyle brain health management and versus those only brain health educations. So we found that tailor-made lifestyle brain health management was associated with improvement in control of risk factors, resulting in improved cognitive performance when comparing with the controls receiving only brain health education only. And then we further demonstrating that among the cognitive ICOV positive and ICOV negative, the ICOV positive results have a mean increase of 1.8 point in brain health was association with a risk reduction of cognitive decline by 43.7%. So because of the time limit, I'm going to skip the existing gap and more focusing on the future directions. So we would like to suggest to move forward evaluating whether economics can meaningfully improve clinical decision making, downstream patient outcomes, and the overall benefit harm balance of care. And we also suggest to develop multimodal AI models, for example, including OCT, that leverage the unique advantages of different modalities in ophthalmic imaging. We would also propose to design whether the tools are positioned for risk stratification, pre-screening, triage, or monitoring, which has important implications for regulatory classification, labeling, and the level of evidence required. So in conclusion, AI-driven oculomics represent a promising approach for assessment of brain health, early identifications of Alzheimer's disease risk, and monitor retinal brain changes over time. So realizing this potential will require interdisciplinary efforts in standardization, population definition, workflow integration, infrastructure development, rigorous evaluation, regulatory alignment, and also ecosystem development. So I would like to add with thoughtful implementations, so we believe that oculomics have the potential to transform brain health assessment, particularly towards dementia prevention. I would like to acknowledge my team, my collaborators in Hong Kong, in Singapore, and also in China. Thank you so much for your kind attention.
A wonderful presentation, Dr. Chung. Next up will be Dr. Nemo Patel from the Massachusetts Eye and Ear Infirmary and Harvard Ophthalmology, and he will be speaking about AI for sickle cell disease.
Hello, I'm Nimish Patel. Thank you for allowing me to present today. We're going to be talking about artificial intelligence for the detection of maculopathy in pediatric patients with sickle cell disease. I'm from Mass Eye and Ear, as well as Boston Children's Hospital, which is part of the Harvard Medical System. As we learned in medical school, sickle cell retinopathy can be caused by an inherited blood disorder. Sickle cell disease causes sickling of the red blood cells, which can constrict the blood vessels, leading to hypoxia, obstruction, ischemia. This can cause vaso-occlusive disease in the retina, as well as the brain and the rest of the body. There's a variety of different classifications for sickle cell retinopathy, including the Goldberg classification, which ranges from arterial occlusions to retinal detachment through neovascularization. A lesser recognized entity is sickle cell maculopathy. This is where you can get localized macular thinning, usually in the temporal area, that's not always clinically apparent on fundoscopy, and it's more easily detectable on OCT and OCTA. Some of our prior work has actually demonstrated that this can be visually significant through microperimetry loss. We established a cohort of pediatric patients with sickle cell disease, and we found that temporal retinal thinning was quite prevalent in as much as 1/3 of the patients. Not only that, it was progressive with more thinning over time. Moreover, we then established that this macular thinning can also be tied to systemic disease in the rest of the body and the potential for the eye to serve as a biomarker. It was the first known study to examine quantitative OCT and OCTA parameters and assess systemic outcomes. Particularly the thinning of the retina and the loss of the vessel density and the deep capillary plexus was associated with severity of systemic disease. That was measured by things like stroke and ischemic events. We concluded that quantitative measures obtained from multimodal retinal imaging could provide a valuable non-invasive biomarker for assessing systemic disease activity in pediatric patients. And the reason why this is important is a lot of these patients, especially the young patients with sickle cell disease, have a very severe form. This leads to frequent hospitalizations, missed time from school, caregiver burden, a high cost to the patients and the health system, and long-term sequelae. So our question was, can we put all this together and start to integrate artificial intelligence? We wanted to assess the feasibility of AI algorithms using OCT images to automate the screening and diagnosis of retinal thinning in children with sickle cell disease. And in the future, could we use AI to predict these systemic outcomes just from the OCT or OCTA? And we think the reason that this could be important is that all these patients are presenting generally to a doctor at his sickle cell visits. So there's a need to decide who to refer for ophthalmology evaluation and who may not. So this is our cohort. It was a retrospective series of patients who are less than 18 years old with sickle cell disease and who had an ophthalmic exam. This was from 1998 to 2022. We used the OCT on the Heidelberg to get qualitative as well as quantitative data, and we also had an OCTA on the same machine. We extracted two different scans, and there was some thought into exactly how to do this for the AI and how to train the model. We initially took these cuts right through the center, but as we went along, we realized that it's not just temporal thinning that's important in sickle cell disease. It's actually mostly superior temporal thinning. So we couldn't just take the singular cut through the macula. So we decided to feed the algorithm two cuts or two images, one through the fovea and one through the superior temporal area as well. We then partnered with a group at Boston University. We were very thankful to have these collaborators. The lab was run by Dr. Pinsky, and he had a team of graduate students who were very interested in artificial intelligence. And they helped to design predictive models testing three different machine learning algorithms. One was a logistic regression, one was a nearest neighbors approach, and one was a random forest. These are different types of algorithms that assess various methods of machine learning. We wanted to look at classification accuracy, as well as sensitivity, specificity, F1 score, and area under the curve. These are our results. We had 87 patients, a total of 174 eyes, and pretty balanced throughout the groups. We had the majority of sickle cell SS. And then you can see here on the different models, the different levels of accuracy. We found that there was a little bit higher as you went to the random forest model and had higher cross-validation accuracy as well, with very high sensitivity and specificity, precision, F1 score, and area under the curve. Because we had low numbers, we had to duplicate some of the dataset values to generate the high numbers to train the algorithm. The random forest algorithm outperformed both the KN and logistic regression algorithms. Analysis of the individual retinal segments demonstrated superior diagnostic accuracy and was able to accurately identify sickle cell maculopathy using OCT imaging. There is a potential clinical impact for this condition, so our thought is that these OCTs could one day be put in a sickle cell clinic, which could help decide which patients need to be referred, as we know that sometimes the OCT can correlate to the peripheral retinopathy. Moreover, as things get more advanced with sickle cell treatment, it's going to be really important to understand who has severe disease. In the systemic issues, we really don't have good biomarkers for systemic disease progression. They're using really indirect measurements like transcranial Doppler ultrasounds for strokes, while in the eye, we have very sensitive metrics like millimeters of thinning of the retina. Some of the limitations include this is a single center, single data set retrospective design. And one of the future implications is this gene therapy, which I alluded to. It's got a 95% functional cure. However, it does require myeloablative conditioning, which includes high-dose chemotherapy. this carries a significant risk of infection, infertility, and secondary malignancy. So it's very important. We need to know who to treat. And I think now that we've used AI to detect maculopathy, I wonder if we can use AI to start predicting who's going to progress and who could be good candidates for gene therapy. So in future directions, we're looking at other imaging markers, OCTA, microperimetry, choroidal vascular index, larger database research, and prediction of systemic outcomes. Thank you for your attention. This is my contact information, and I want to particularly thank all of our team members who did a lot of work on this, our research fellows, as well as Dr. Pinsky and his lab at BU.
Well, that was a really interesting talk about the use of AI for detecting sickle cell disease in kids. Next up will be Rania Habash, who'll be speaking about ambient oculomics. Rania.
Thanks, Ted. Thanks for including me here in this panel. I'm really excited to be here with these superstars. Okay, well, we're going to talk about a topic that, really gets me out of bed in the morning. This is ambient oculomics. So I'll try to control my slides here. Here we go. Yeah, here's the delay everyone's talking about, huh? Okay, good. So what we want to do now is try to use the eye and the periocular region for repeated signal capture. That's really where the magic is, right? So we have to get all of these different biomarkers, interpret them in context, and then that gives us really meaningful prevention and detection knowledge for patients. So we just talked about some of the different types of oculomics. A lot of this really has been centered on the retina. The retina was sort of like the foundation layer for all of it. So I'm not going to spend too much time on that because my colleagues really covered that very well. But this is the oculomic signal stack. This is the layered system that we need. We can do way more than just the retina. We can also do the external and periocular regions, dynamic ocular behavior or psychometric analysis, and then physiologic overlays, which is really what I've been working on most lately. And that's RPPG and looking at different metrics from underneath the skin around the eye. So this is a layered system because the value comes from stacking all of these signals together and then putting them in context and then trending and looking at longitudinal deviations for our patients so that we can really get a good assessment for what their overall health is doing. So where do ambient signals actually come from? And I should probably stop here and tell you that if you haven't figured out already, ambient oculomics means getting these measurements or getting these signals without trying, without any active attempts. This is just stuff that you use every day, just doing things every day that can actually derive and extract these signals. So something as simple as, a phone unlock, like a Face ID, that can actually give us a lot of information. The pupil, RPPG signals, gaze, blink rate, things like that. If you're doing a video call or a selfie or even a talk like this, there are a lot of metrics we can also extract, the same types of metrics. For screen and text images, things like fixation or saccades, this is the psychometric part of things. And then lately, there have been smart mirrors that are coming out now so that, when you're brushing your teeth in the morning, you can also collect signals. So basically, now the clinical exam moves outside of just the office and it starts to become an ambient type of experience with all these, like a series of these tiny measurements which are collected all day long doing your normal everyday stuff. That's the real power of all of this. So how does the signal extraction work exactly? So first we capture the image, and that's, using the laptop or the mirror or whatever. Then we localize it, right? So we have to zone in or hone in on the parts of the face that we really want to analyze. Then there's some normalization involved. That normalization is really important because patients can, I'm so sorry, my dog is barking. 1 second, I'm gonna let him out. So he doesn't keep doing that. Okay, I'm back. Sorry about that. Okay, so the next thing that we need to do is normalize things. So if a patient is moving too much, for instance, that there needs to be some stability there. Things like illumination correction, even the auto adjustments of the camera are things that we need to normalize as well. Then we can extract the signal. And when we do that, we're looking at different things. We're looking at color, the texture, the waveform or the gaze trajectory, and pupil dynamics, things like that. We're going to get into that a little bit later. But after all of that is extracted, it's really important that we apply gating, like quality gating, to this issue. So we have to look at signal to noise ratio, we have to look at motion, lighting insufficiency, things like that. And we really can't project an answer or an output until those quality gates and thresholds are met. Once that's all done, then you trend it. So, you want to measure this against a patient's personal baseline, because that's what's going to give us like our statistically meaningful changes and insights, right? You don't want to do point measurements. You actually want to do trend measurements instead. And so if we use this entire system, what happens is, with the quality gating, with the longitudinal baselines, this becomes a bridge from just, point signal collection to actual clinical use. Okay, so I'm not going to spend too much time on the retinal stuff because all my colleagues covered that awesome. But it's important to note that this was the foundation layer to everything. I still remember reading the Google paper in 2018, and I was blown away by it. But, without even asking, it started to, I'm sure everyone here is familiar with this paper, but it started to actually identify the gender of the retina that it was analyzing. And nobody knew really how it was doing this. I mean, we weren't even trying to extract that kind of information, but it did it with an AUC of 0.97, which was high. So so that was like the very first time we realized that, hey, maybe there's a lot of signals that we're not actually seeing. We can't see with the human eye, but they're there. And so I wanted to use this because what happens next is, I'll skip this really quick. But what happens next is we can look at different regions, not just the retina. Now we can start looking at things like the forehead, the eyelids, the conjunctiva, things like that. And this is really important because another Google paper actually showed that the external eye can hold a lot of information that we didn't even realize it could. The takeaways from this paper were as follows. First of all, it wasn't just looking at one portion of the external eye. It was looking at all kinds of factors, things like the eyelid swelling or facial puffiness, periorbital edema, things like that. But the really interesting thing that came out of this was that color was not that essential. So it wasn't really looking for a red eye. Even in grayscale, it was able to pick up things. For something like hemoglobin or anemia, that signal was actually really high, which was very surprising to everyone. Because again, it wasn't looking at pallor, conjunctival pallor. It was actually looking at way more than that. We're not really sure even what metrics it was looking at. But again, a very good signal there, as well as liver scores too, like AST and thyroid, of course. So this opens up a whole new era where we can do way more than just retinal biomarker extraction. Now we can do things like, fixation, blinks, saccades. And I think, based on Carol's excellent talk on neuro stuff, I'm going to just fast forward in the interest of time. But I'll point to a couple of other really interesting things when it comes to psychometrics and pupil dynamics. I don't think we covered this, but things like autism, for instance. We know kids with autism, they have trouble fixating, right? So you show them a picture on the screen, and now all of a sudden, you are able to, first of all, screen or diagnose possible atypical fixation patterns, for instance. But then what about training them? So now we can actually train them to fixate or focus better, right? Another really interesting one that comes up is depression. If you show a patient with depression a picture of, kids playing with a balloon, right? That would probably make all of us pretty happy. And the pupil is supposed to dilate when it sees an image like that, a really positive or happy image. But in patients with depression, it doesn't do that as much. That blunted dilation gives us information. So now you're seeing how these things all come to play to create a really interesting picture of a patient, not just from the typical means. This is where I've been spending a lot of my time, actually. So this is our PPG, remote photoplethysmography. So imagine now taking a selfie or a video call or some sort of picture of the eye. And we can actually unlock lots of information from the blood vessels under the face, under the skin. And that's from the RGP portions. So it will extract different things like the pulsatile patterns, the speed of blood flow through those vessels, the vascular tone, the autonomic state, things like that. So we can actually extract things like blood pressure, oxygen saturation, things like that, which we never could before, just with a front-facing camera. It's pretty amazing. Now, there's a couple of caveats there. We found that, for instance, when women wear foundation, sometimes that will, change the pattern a bit. Also, if you're doing Face ID, 3 seconds is a bit weak for the model, so that you have to have signal quality, quality gating and signal noise ratio gating as well. But the point is that with a selfie, we're able to look at these blood vessels under the skin, and that is super exciting to me. Again, going through some of the RPPG stuff, I'll gloss over this a bit, but what was really important that we saw was that demographics was informing these models tremendously. I mean, like probably 50% of the time, the model was extracting the waveforms, but then using demographics input as well to strengthen that model. And so it's not just the pure waveform, but demographics are really important, which is, basically the same thing we found out in the retinal foundational work that has been done. That's also, that presents the opportunity for the guardrails that we need. For instance, we need patients of darker skin tone and different ethnicities to train these models as well. And then you put it all together, right? So the eye is not the only omic that we should be extracting. We should be getting, the eye has rich data, right? But there is a bridge now to the rest of the body, as we heard. And we should be integrating with things like wearables, smart mattresses, voice. Voice is a super exciting one. So now imagine, having prosody, for instance, which is the tremor of the voice, and adding that to the psychometric analysis for the oculomics. Now you've got a much stronger, like, multimodal signal for neurologic disease. See, and smart scales, of course, give us metabolic information now. So putting all of these things together, we get a beautiful picture. I mean, now just imagine a day in the life of ambient oculomics, right? This is how the signals accumulate through the day. You wake up in the morning, you open your phone, right? That's one of the first things we all do. So now it's getting that information. We brush our teeth in the smart mirror, and it's adding more information. We're working during the day on our screen, more info, video calls, and then combining that data to aggregate with wearable data as well, the Aura Ring or the Apple Watch or whatever. And now you've got a really nice clinical picture. Then you apply like a dashboard, which is now trending things and keeping humans in the loop too. So that's the real magic, just making this repeated, trending and effortless for our patients. So I will end there. Thank you so much. I really appreciate it.
Wow, that was a really interesting picture you painted there, Rania. Next up will be Peter Campbell from OHSU, who will be talking about AI-derived vascular analysis for ROP. Peter.
Thanks, Ted. Honored to be here. I'm going to take this in a different direction than some of the other oculomics talks. And that's going to be what we can learn by applying quantitative methods, not just about the eye disease, but about the disease epidemiology and even potentially pathophysiology. And I'm going to make the thesis that measuring vascular severity in ROP is actually a surrogate for intraocular VEGF levels. So I'll come back to that. Sorry, these are my colleagues in the IROP Research Consortium. I do have a disclosure in that we're commercializing the AI vascular severity score. So just as a background, our group has done a lot of work measuring vascular severity in retinopathy prematurity. This turns out to correspond to not just the spectrum of plus disease, but actually turns out to be a surrogate for the overall level of ROP in an eye. And specifically, it's because as the stage goes up, the vascular severity score goes up. And interestingly, this was from a paper in 2020, for a given stage, the more posterior zone, which is more severe, the vascular severity goes up as well. And that was a new finding. So what it means is that as the vascular severity goes up, the overall level of ROP is higher in an eye. We also know that phenotypes vary in ROP around the world. This was actually a big emphasis of the last international classification of ROP, is to acknowledge this. On the left is an image of aggressive ROP, which used to be called aggressive posterior ROP and now just called aggressive ROP. And on the right is an image of aggressive ROP from India. And working with colleagues all over the world, it's become clear that even though the same underlying risk factors are present, the disease phenotypes can look a little bit different. And to oversimplify things slightly, a lot of this is related to differences in primary prevention and the ability to titrate and monitor oxygen. And I'll come back to that idea. But the question, the motivating question for this project was, does the relationship between vascular severity and zone, stage, and extent of ROP remain the same across populations, even when phenotypes appear to differ? And so to answer that question, we looked at two data sets. We looked at our data set, which was North American babies, predominantly academic medical centers, about 6,500 exams, over 1,000 babies. And then we looked at a year's worth of data. This is a typo, it was 2019 to 2020, 8,000 exams to 2,600 babies from the Aravind Eye Care System. This is from a large telemedicine program in South India. We applied the same methodology, which was putting all the images into the algorithm, and it outputs an eye-level vascular severity score for images that pass certain quality thresholds. When we looked at the demographics, not surprisingly, the demographics were different. In India, the babies are older and bigger, and that's true not just for the overall population, but for the treated population. So babies in India are treated who are at lower demographic risk. And again, this is thought primarily to be due to differences in underlying ability to titrate and monitor oxygen. The key finding from the paper was that although there were differences in demographics, the key relationship between zone, stage, and plus remained the same. That is, as the stage went up, the vascular severity score went up, and as the extent of disease went up, the vascular severity score went up. And as you had a given stage, the more posterior disease was, again, the more severe it was, the vascular severity score went up as well. So despite differences in phenotype, the overall relationship remained largely the same. What was interesting, though, was that for a given zone stage combination or category of disease, say zone 2, stage 2, the vascular severity score was lower in the Indian population. So although the overall relationship was the same, the actual equation converting these X and Y variables was different. And so that raised the question, why? Well, to think through that, we sort of went back to the underlying disease pathophysiology and came up with a unifying hypothesis. We know that in phase 1 of ROP, hyperoxia causes vasoconstriction, et cetera, suppresses VEGF levels, et cetera, leads to ischemic damage. And then in phase 2, so-called, it's actually a hypoxic problem that leads to increased VEGF, neovascularization plus disease, et cetera. We know that in phase 1, if you have higher oxygen exposure, you get bigger babies getting ROP, and that's exactly what we see in low and middle income countries. So we suspect that is part of the demographic reasons for these differences. We also know, however, that if you have higher oxygen in phase 2, it may be protective. There's good data from preclinical models in oxygen-induced retinopathy. There was the STOP-ROP trial that some of us remember from the 90s, which failed its primary endpoint, but only barely, and suggested that in phase 2 ROP, higher oxygen may be actually protective. And so the question became, what if the vascular severity score in phase 2 reflects the effects of higher oxygen exposure between the populations? Well, that would give us 3 testable hypotheses to try and figure that out. Number 1, populations similar to the US demographically and neonatal care-wise would look more like the US data. The equations would be similar. Number 2, a stop-ROP-like intervention where you randomize babies in type 2 to higher oxygen would lead to a lower vascular severity score. And that could be tested. Or 3, temporal changes in oxygen management in a population would be observed by changes in vascular severity in severe ROP. And it turns out we can test that last one. And so let me explain what I mean by that. I showed you that the vascular severity score is a surrogate for the overall level of ROP in a baby. And if you multiply that by all the babies in a NICU or in a region or in a state, you can get a surrogate level of ROP for the population. We previously showed, this was a paper in pediatrics a number of years ago, that higher hospital level ROP severity correlated with lower ability to titrate and monitor oxygen. We further showed a few years ago that this has been improving in South India as neonatal care has been improving, so that babies with a given demographic, given birth weight, gestational age, are at lower risk now than they were before of developing severe ROP, primarily due to improvements in oxygen management. And so if the vascular severity score is lower in phase 2 because of higher exposure to oxygen, and oxygen management has been improving between 2015 and 2020, then the eyes of babies with severe ROP should be lower in 2015 compared to 2020 in the Yerevan population. And so we were able to test that by looking at these data sets. Here's aggressive ROP in the US data. Here is aggressive ROP in the Indian data in 2020. And here is aggressive ROP in the Indian data in 2015, confirming that hypothesis. So in summary, higher vascular severity score is associated with more posterior zone, higher stage, and higher extent of stage 3. For a given zone stage, the vascular severity score is lower in India versus the US, although this difference is narrowing over time. And these findings are consistent with the hypothesis that the differences are primarily oxygen mediated, and that VSFs may actually be a surrogate biomarker for intraocular VEGF in severe ROP. Thanks so much.
Wow, that's a really interesting talk you gave there, Pete. Up next will be Nazli Zeberdas from Mass Eye and Ear, who will be speaking about AI for ophthalmic disease, deep phenotyping, and genetic discovery. Nazli.
Great. Thank you very much for the kind introduction and for the invitation to speak today. My disclosures are shown here, none of which are relevant to this talk. So we all practice personalized care to some extent. So as a glaucoma specialist, I might take the central corneal thickness into account when determining the level of intraocular pressure to set for the patient, their level of anxiety, and their demographics in choosing the type of surgery. However, most of these treatments are designed for the average person, and this is not very precise. Precision medicine is the idea that humans are diverse and diseases are complex, and we need to abandon this one-size-fits-all approach and consider differences in genes, environments, and lifestyles when we're recommending treatment for our patients. There is a slight lag. So, it's clear that advances in glaucoma genetics, or genetics in general, will allow for more appropriate care of our patients. We do know that glaucoma is actually one of the most heritable of all complex human diseases, and to date, hundreds of risk loci have been identified for primary open-angle glaucoma. However, each of these variants only give us a small explanation of the disease risk. So we know, for example, that if we add these common risk variants together, we can understand how the disease risk changes. So if you have one variant, for example, it tips the scale a little bit towards disease. And if you have many of them, it tips the scale a lot towards disease. And we call this a genetic risk score. But despite knowing over 300 risk variants for primary open-angle glaucoma, for example, just as a disease that we're most interested in studying at the moment, the AUC can never seem to pass 0.75. So it's still very limited. And the question is, why is that the case? Well, for complex diseases, we know there's influence of environmental and systemic risk factors that are not completely understood. But also importantly, the genetic architecture of glaucoma is not fully understood. So the question becomes, how do we improve gene discovery? And this is really where AI comes in. So we can use endophenotypes. Endophenotypes are heritable quantitative traits that provide a continuum of disease risk and can improve our detection power in genetic studies. Clinical endophenotypes like intraocular pressure, cup-to-disc ratio, central corneal thickness have been previously used to identify variants for glaucoma, but there remains a major gap. There is an emerging field of imaging genetics where we can use structural correlates of disease as defined through large data image analysis to identify structural correlates of the disease and identify novel genetic risk variants. And our group has been using unsupervised machine learning methods for this very purpose. The rationale for this in glaucoma comes from the idea that glaucoma, even open-angle glaucoma, is really not one disease. Stephen Drance recognized that there's structural and functional variations in primary open-angle glaucoma. So we use this idea to take retinal thickness maps, and first we need to understand what are the phenotypes in a clinical data set. So we take our large data repository from the Mass Eye and Ear data set and use unsupervised ML models to identify different patterns among glaucoma patients. Then we have the ability to take these trained models and transfer them into a biobank. These large biobanks, even though they're not rich in disease phenotypes, are rich in genetics. So we can then extract these same vectors and perform genetic analyses. So for example, in the first method, this is an autoencoder method that we have used in the past, where the model's task is to essentially reconstruct the image. And we can take the feature vectors, which are the most important parts of the image or parameters the model is paying attention to, perform dimensionality reduction, and then clustering. We can additionally use a semi-supervised or self-supervised method called contrastive learning, where we essentially increase the similarity between positive pairs of images and decrease similarity between negative pairs of images, and then pass that into the encoder to extract the feature vectors. So I can show you there, how do we decide how many different clusters there are? Well, there is some subjectivity to this. But we can use some statistical parameters like AIC and BIC to determine the number of clusters. So for example, using our first method, we find 11 optimal clusters with some examples of the images shown here. These are macular OCT images from the UK Biobank. These are 9 optimal RNFL clusters, for example, that you can see here as well. And then we want to know if our data transfer actually works well. So does it make sense to go from one data set to another? So we look at the reconstruction error among the two different data sets. And you can see that the reconstruction error is fairly low and similar between our clinical Mass Eye and Ear data set and the UK Biobank. For our momentum contrast method, we find 11 optimal clusters for the GCC layer, and then 11 also for the RNFL clusters. And then I'm going to go through this. So again, we want to make sure that these work across our data set. So we look at the correlation in the feature space between the Mass Eye and Ear and the UK Biobank clusters. And you can see that there is good correlation. So we know that the transfer is successful. And then finally comes the genetic analysis. So then we take these ML phenotypes and we can perform GWAS, or genome-wide association study. And if you're not familiar with a Manhattan plot, this shows the chromosomal position as a function of negative log 10 p-value. And each of those spikes is a locus. And you can see that there is multiple hits that are coming up here across the phenotypes. What we want to know is if this is determining whether there's any novel association. So we can look at previously discovered genetic variants across glaucoma and related phenotypes. And we can see that 2/3 of what we are finding are previously described, but about 1/3 of them are novel, which is pretty exciting. Then we want to make sure that this has biologic meaning. So we look at cell type specific expression of the genes, and we can see that the genes that we are finding are pointing to relevant eye tissue. So for example, the optic nerve head, as well as the ganglion cells. These are some examples of the novel genes that we are able to identify using our ML method, and we can look at the biologic plausibility of these along multiple levels of evidence, and some of these are particularly interesting candidates for glaucoma pathogenesis. So this is just the beginning. There's other ways that we can define phenotypes. So currently we're working on functionally guided structural phenotypes. So we can use visual field data to better define our structural endophenotypes for GWAS. We can look at progression patterns and look to see whether we can identify or use those for gene discovery. We're also using natural language processing for better precision phenotyping and genetic analyses. And I'd like to thank everyone who has contributed to this, funders, as well as my collaborators. Thanks very much.
Wonderful. That was our last presentation for this meeting. I'd like to invite all the speakers who are still with us here to unmute and turn on your cameras so we can have a short panel discussion. As people are popcorning up here, I'll ask Mike first. I'm really excited to see such a powerful tool that you've been developing at Toku. I saw on one of your slides your clinical trial is already completed. So how long until we actually see the product on the market, and what are the barriers, I think, to adoption, to getting, primary care or optometry or, CVS, or where are you going to put this thing?
Great, tough questions. Yeah, so the next phase is FDA clearance, and as you know, that's largely up to the FDA. Typically the quickest that can happen is sort of the 3 to 6 months period, but often for more novel areas like oculomics, it can take longer. So we don't have the answer yet to that. On the other, I think, a couple of big things around deployment or implementing. We have successfully deployed our biologic age assessment in optometry clinics and some longevity clinics. So I do think there's a very big untapped opportunity there, because retinal imaging is being, retinal fundus photos being done more and more. But I think that, the bigger for many things in the AI and digital health space is around reimbursement and what are the financial models that ultimately, provide an incentive for the providers to implement and to make it a sustainable business so we can, keep providing this and keep developing, other new products. So.
Thank you so much. I'll transition over to Rania next. Rania, it's a very futuristic presentation you give about, just harnessing all the different technologies that we've been seeing in oculomics and just making it kind of in the background, almost like, Dr. Eric Topol likes to talk about these twofers that you get when you do chest x-rays or CT scans in the ED. You're talking about, using your phone in your daily life and then getting health data from that. What do you think are the next, near-term challenges to actually, bringing a product actually to the customers in this field?
Well, I will start by saying there already are products in this field, and that's exactly what I'm working on. So there is a product. It's a beta, but there are other products that are there, not quite as much yet, but it is here. I mean, this is not science fiction. It's not that futuristic. I mean, it just needs further development. But yeah, I mean, it's here and ready to deploy. Now the next thing is, number one, the first hurdle is nobody believes it, and even us, right? And we're all early adopters. But number two, the main thing here is that now we want to move beyond just what we've developed as a product and what we can actually use in real world. Because in the real world, yeah, women wear makeup and it changes that reflection pattern, or there are different, skin types which may not read quite as well. But that speaks to the importance of trend data rather than just point measurement too, because now we can start making assessments versus a patient's baseline rather than just a point in time.
Thank you so much. Pete, I was really struck with the amount of correlation that you were able to show between the vascular severity scale and essentially the VEGF level in these eyes. In our clinical lives, for those of us who provide adult care to patients with VEGF-mediated diseases, we tend to use OCT as our VEGF meter. Have you thought about, now that I heard that there's a new handheld OCT device that's coming out now that you could use potentially in NICUs. Is there any thoughts of trying to add that dimensionality to your data set and trying to correlate with that as well?
Yeah, thanks for that question, Ted. I do think we'll have handheld OCT on the market in the next year. It turns out in OCT and ROP, it's not quite the same as in adults. I know with our DME patients and we'll see that fluctuation that sort of corresponds to when they're wearing off or whatever with anti-VEGFs. In ROP, at least in the macula, the macular edema phenotype in ROP doesn't seem to be quite as VEGF responsive, but I don't think we know the answer to that question. Certainly the dilation tortuosity phenotype does seem to be correlating to VEGF. And so I think we have a lot to learn, but it'll be just like all that we've learned in the past 15 years with adult OCT and questions we didn't know to ask. I think we're going to see the same emerging knowledge in pediatrics.
Thank you so much. And lastly, with Nesli, I really thought that the correlations you made between the OCTs and the risk scores for glaucoma were really remarkable. And you mentioned that you were going to incorporate other data fields such as visual field data. I know some colleagues are taking anterior chamber fluid, like say, for example, during cataract surgery, and doing proteomic analysis of that. Is that a potential additional data point that you could incorporate into this multimodal analysis?
Thank you for the question. I think that's very interesting and growing fields, both proteomics and metabolomics. I think right now with the advent of biobanks and large amounts of multimodal data, including imaging, EHR data, metabolomics, proteomics, we can understand what I envision really clusters of disease better. And this is not just for glaucoma. I think it's for most other diseases that we treat, complex diseases. We lump them all together, when in reality, people have very different phenotypes and probably very different responses to therapies and very different course.
Wonderful. Well, that's all the time we have today for our annual Ophthalmic Artificial Intelligence Summit. I'd like to thank all of the speakers and the panelists and the moderators and my co-directors for running such a wonderful program. Especially like to thank iVista Medical Education for running this for us. And lastly, also like to thank our wonderful supporters. Those are Genentech, Apellis, Regeneron, and Topcon Healthcare. We hope to see you all next year, and we'll be here. Thank you again.
Thank you.
Thank you.